Hello, good evening, everyone. I'll take the session.
Hello, good evening, sir.
Uh, shall we start?
Yes.
Okay. Okay.
Guys, I can't hear anything. Can you hear?
Hello.
Hello.
Yes. Can you hear me?
No. Yes.
Now it's
Yeah.
Thanks.
Okay. Okay. So first is the first is
So just one question before you start.
Mhm.
The doubts are we going to ask after you complete, or can we ask in between?
you can ask him.
Okay, thank you.
So first we'll have McCulloch-Pitts neuron. So MP neuron. Okay. So first MP neuron have two kinds of inputs. One is kind of denoted by arrow, which is we call like exhibitory uh, input, and then another is denoted by this round at the top, which is inhibitory input.
Exhibitory or excitatory?
I think it is in exhibitory only. Okay, not. Okay, mental. Excitatory. Okay. So excite. Uh, excite.
EXCI. I mean, yeah, inhibitory and excitatory. Yeah.
Inhibitory. Okay. This is so there's two kinds of inputs will be there for MP neuron, and so let's say this is a NP neuron, and if any of the inhibitory input is on, so this is inhibitory input. So if I like so small, so if any of the inhibitor input is on, so let's say let's rest, anything can be there. Okay, then the output will be 1. Okay, output yes.
If it is on, it will become 0, no, sir?
Zero. Yeah.
Oh, sorry.
You're talking
If
about
any
inhibitory being on,
okay,
right?
yeah, that's what the meaning. Okay, sorry. If any of this, so if this is on, correct. So opposite of that, then it will be 0. Okay. So if any, like here it's given 1, but any given to you, but any one if it is on, which is 1. So this all can take values from not from, but just 0 and 1. Okay, all of them, either 0 or 1. So all of have input of 0 and 1 in McCulloch-Pitts neuron, and of course y, which is output, will be also in either 0 or 1. Okay, so if any of this inhibitor input is on, then you'll get 0 output. Okay, rest for rest of them, you have to figure out the threshold. Okay, so then comes the theta parameter, that what is the threshold of this MP neuron. So if we look into the function, so we just sum up all the inputs. Okay, so whatever inputs we have, we sum them. So of course, like it makes sense if we have this excitatory inputs, then the sum is going to be some meaningful. Otherwise, so let's say if this is 0, then it will not add anything here, right? Nothing it will add to the summation. If it is 1, then we don't need to do the summation, we just give output as 1. So when all this excitatory inputs are there, then we are going to do the summation, and then we'll figure out what is the threshold we wanted to keep. So we can keep some threshold and then say that, okay, above this threshold, this MP neuron will going to give output as 1. Okay, and if it is less than theta, then output is going to be 0. Okay, so if all of them are excitatory input, then you can do it, right? Then you need to add them up and then figure out the theta of that, right? So let's say if you want to implement AND function, okay, and so this is my McCulloch-Pitts, and I have 3 neurons. Okay, so you can see that from 0 0 0 0 0 1, you can go till 1 1 1. So this 8 kind of inputs will be there, and you know that if I write y, all of them is going to 0 except this last one, right? So this last one will be 1. So that means I need something where I add like x, so we can call x1, x2, x3, right? Should be greater than equal to this value, then only they should excite, right? Or give y equal to 1. Then only it will give that greater than 3, then only it will give y equal to 1. Okay, so that's how we can set the theta from this. So all of them are excitatory, that's why I am summing up and doing it. So less than 3, you can see all of them. So there will be no scenarios where we can get sum equal to 3, right? So here there is nowhere we are getting 3 ones, right? So it's always going to be 1 0 of them, right? Any one of the x is going to be 0. So that's why we can set theta is equal to 3 for this case. Or if we say, let's say another example could be, let's say OR function. Okay,
Theta
so
would be
let's say
1.
yes. So we can take for 3, okay, for again, and we'll have starting from 0 0 0 to 1 1 1, right? So all of the cases, 8 of the cases are written inside this. That's it, and we need uh, any one of them to be 1, right? So first one will be 0, but rest all of them will be 1, right? Y output is going to be 1. Okay, rest all of them. Okay. So in this case, I need something where, let's say x1 plus x2 plus x3, if I do, then it has to be for this case, it needs to be less than that theta. Right, and then for rest of them, my summation of xi should be greater than this theta, and we can set equal to 1, right? So if it is greater than 1, then we can so in this case we can set theta equal to 1 and we can solve this problem, right? So less than 1, so here it is, so all the sums are 0 and it is less than 1, yes, so it will not activate this, excite this neuron, right? Then if it is more than or equal to 1, then only we'll get output as 1, right? So then what is NOR function? If we see NOR function, let's say I have this, so how will I make a NOR function? I want opposite of this, right? So this is OR, not of OR means let's say if I write pi bar, then I want 1 here, but rest all should be 0, right? That's what NOR is. So how will I do that? I can put, let's say, any of them as sorry, all of them as inhibitory inputs, right? Then I can have it. So if any of them is excited, so if any of them get excited, then I'll get 0, right? Which you can see this 7 cases are there where at least 1 is excited, correct? And I'll get zeros. So at least 1 case left where all 3 of them are 0. Okay, so x1 plus x2 plus x3, which is 0 plus 0 plus 0. So in this case, I need to set some theta so that it will activate this neuron, right? So that is going to be 0, right? So in this case, my theta is going to be 0. Otherwise, it will not give output at 1 for all of them 0, right? So that's how MP neuron works. Okay, very simple.
Sir, if I put a inhibitory variable as one of them,
Mm-hmm.
sorry, sir, this is the inhibitory variable, right? 1, 1, 1.
Mm. Yes. I'm giving input as 1, but this is inhibitory variable. Yes, inhibitory input. Yes.
So x1 plus x2.
This is only I'm doing for one case because rest all I'm having
this
one.
this is NOR, right? This is, sorry,
This is
I'm
not. This
confused.
is not. This is not. This is OR. I did
Correct.
NOR, and
Okay.
if any of them is 1, any of them, okay, I wrote 3,
Correct.
but any of them I'll get 0 as output. Okay.
So threshold is basically
You will set for excitatory inputs only.
Yeah, threshold will be 0 if it's less than, no, threshold should be, so when is this output 1? Output is when all the inputs are 0, right?
Yes.
Right. Then the
Yes.
threshold should be
this, right? So summation, you got this. So you want equal to this, or this value has to be greater than whatever theta you decide. So theta, I mean, you need to have theta.
Correct.
From which the
Theta is
summation has
equal
to
to
be
0.
greater than equal to. So if I set theta equal to 0, then this will work.
Okay, got it.
So I have one question, sir. This so that means some Boolean functions have to have an inhibitory this.
Correct. For
It is
MP neuron, yes. For MP neuron, yes.
okay.
This is MP neuron.
So,
We will not need this same thing in Perceptron, so which is next algorithm. But MP neuron will need this inhibitory input to represent some of the functions. For example, NOR function, NOT function also will require this inhibitory input.
okay.
Suppose because we represent as, we can't take a minus, right? Minus is not allowed.
No. For now, weights are not there. So we just taking summation. That is the basic thing about MP neuron, that this is the only thing. If you when W will come into picture, then you can take minus and all everything. So for now we are just summing up them. If there is any inhibitory input, then we'll just put it as 0 if it is on.
Okay, just one question, just theoretically. So the basic definition we have that W1 plus X1 plus X2 plus X3 is greater than equal. Can I change that to represent NOR? Then I don't need inhibitory. Suppose I'm allowed to change that. Then I don't need inhibitory.
Sorry, what? You are allowed to change?
So X1 plus X2 plus X3, if it's greater than equal to theta, then the class is 1, correct?
Okay.
Otherwise it is 0. And we have to determine theta, correct?
Yes, yes.
Suppose am I allowed to change that? Can I make it less than theta? If it's less than theta, it is y is equal to 1. Is that allowed?
No. Then for less than, it is y equal to 0, right? That's what.
No, I'm saying if I can redefine that as if x1 plus x2 plus x3 is less than theta, then y is equal to 1. If it is greater than theta, it is 0. Then I don't need the inhibitory variables, is what I'm saying.
But that is not MP neuron. I mean,
okay.
You have to be something else, like.
Okay. MP neuron that is defined is greater than theta. Okay. I was just wondering if that definition you can change. It's like just left I'm making it right I'm making it left. That's all.
But that won't be MP neuron. This is about MP neuron. This whole thing. Okay. So now, so in MP neuron we had, inputs are Boolean 0 or 1, and output is also 0 to 1. Okay. So this is a function where we give 0 or 1 as input, and we'll get output also 0 to 1. Okay. Then comes the perceptron.
One question before you go to perceptrons.
Okay.
While going through these previous year question papers, I maybe I'm wrong, but I read somewhere some statement saying that it is not necessary to have a inhibitory this thing input for in an MP neuron for to define all the Boolean functions. And that was marked as true. So that's why I asked, because there was a confusion there.
Vivek, मैं निकालता हूँ. You let sir continue. I'll pull out that statement. There are one or two places where we saw that. I'll try and identify that.
Right. Thanks.
The question was a bit different there. It said that you don't need an inhibitory input for all functions, which is correct. You can make functions without the input also. Without the inhibitory input does not mean that all of them can be done without it.
So that all
just means, yeah. So for example, the AND function can be without inhibitory.
Right.
So that is then you can't. That option is correct.
I agree. I hope they put that all in bold or something. Very easy to miss out.
There's one other statement I just wanted to check. It says, maybe just a kind of a simple addition. It says MP neuron model can represent a wide range of Boolean functions, which is true, not all, by appropriately adjusting its weights and thresholds. This word weight should not be there. Now, there's no concept of weights in neuron, MP neuron. At least we were not taught. You can say default weight is 1, but there's no concept of weights here.
Yes, there is no concept of weight.
Yeah, I just wanted to confirm that. Okay, got it. Thanks. Go ahead, sir. I'm just looking at some of the PYQs we solved, and we are looking for that statement. I'll see if what Vivek was referring to. Go ahead, sir.
Okay. So then comes the perceptron. Okay, so which is what we do is we now have weights to each of the inputs. So I have, let's say, x1, x2, and it could be anything. Okay. It has to be greater than, again, you call it as theta, but now we are calling theta w naught also. Okay. So sometimes it's written w naught, sometimes it's theta. or let it be theta. So if you have theta, that means we are talking about threshold, that that this value has to be greater than that threshold, right? But when we bring it to the left side, we call it as bias. It doesn't change much in the equation, like equation is still satisfied, but that's how the naming is. And bias, now we are calling it as bias, like something like this, right? This is bias, and this is like threshold. And yes, so here also again same, when we have this, so what we call is W transpose X, you can call it. So if you do a dot product of W transpose X, you'll have this summation and plus, okay, so now this W naught also, you can actually change it to plus also, because W naught can be negative as well as positive, right? It's not like it has to be the positive value. W naught has a range of like minus, like negative to positive, right? So we write it this way. Okay, that's fine. And if it is greater than 0, then we can say that output is 1. So y is equal to 1. And if this W transpose X plus W naught is less than 0, then y is equal to 0. So that's how a perceptron is. Now we have weights and picture, so we can take weights and all, and decide the maybe a bias, that what could be a bias for this perceptron to
So one question, sir.
satisfy. Yes.
Sorry. You
Yes,
said
yes.
I can take W naught as positive. Then how will it become a bias? Because my W transpose X has to cross that threshold for it to be greater than equal to 0, right?
Yes.
So W naught should always be some kind of a negative value, because if I'm adding up all these other values. Or
Okay,
you're
well,
saying I can take negative weights, then it can be a positive. Is that the thing? I'm not clear
so
about
let's
this.
say let's say, but this is not a positive, right, quantity. Are you considering this as positive or this as negative? This could
I'm
be
considering
anything.
that as
Let's say,
positive. Yeah.
but let's say this is negative.
Mhm.
Then how will you make it greater than 0? You need to add
Right. Then
something
you
which
have to have
is,
a positive.
yeah, something which is very
threshold.
positive, then only you'll
Okay.
have greater than 0.
Clear, sir.
So it
Clear.
depends on the summation. So what kind of summation you get, based on that you can decide this W naught, right? So let's take example in this. So again, let's say I have two functions x1. I have inputs x1 and x2, and what I need to do is, what we can do in this is, can we make and function? So for now, I mean, so okay, so here perceptron, yes, perceptron can take any real valued function. Okay, so not function, real values. It can inputs can be real value.
What about outputs?
But output will be booleans only, so either 0 or 1. Okay, so inputs are, or you can say this is domain and this is range, if you are familiar with this, but this input, and outputs are going to be 0 or 1. Okay? If it is greater than 0, then 1. Less than, if the summation plus W naught comes out to be less than 0, then y is going to be 0. Okay, so let's say if we implement something, and or function or anything, So these are going to be the input, and let's say if it is, let's say if it is OR function, then I'll have 0, 1, 1, 1, right? So in this cases, I need to write all the equation and then figure out what could be my W naught for this. Okay, so equation is this only. So I have to satisfy one of this, right? So here y, since y is equal to 0 given, or you can call this as y. So since y is equal to 0 is given, I know that I have to take W transpose x plus W naught as less than 0, right? And if I take W transpose x, this looks like 0 only, right? W0, I mean x1 and x2 are 0, so doesn't matter what is W1, W2. Here it is, let's say first, then W1 multiply by x2, sorry, W2 multiply by x2, which is 1. And this needs to be greater than equal to 0. Then I need W1 plus 0 plus W0, which is also needs to be greater than 0. Then W1 plus W2 has to be greater than equal to 0. Right? So from this we can kind of figure out that what is going to be theta. So there could be no multiple solution of this. There is not like one solution of this, but you can maybe figure out a range or something like that. So W naught in this case it needs to be less than 0, right? So if we draw maybe number line, so then it has to be here. Okay? Then let's say W2 plus W naught. Okay, so okay, not much. W1 plus W naught, which also has to be
You wrote
greater
W
than.
naught plus W naught.
Okay. Yeah. So basically this equation. So now I need to add them up. So if W naught is less than 0 and W2, so from this I know that from second equation. So I'll write this is first, second, third, and fourth. So from second I can say that W2
W2
needs to be
greater than
greater
0.
than, right? So okay. Then W1 also needs to be greater than this. From third I can say.
So
And
W2 has to be greater, right? Strictly greater. You can't have it equal to 0 as well. Okay, my bad. Yeah, you're writing W naught. Okay.
yes, this is W naught. Or you can, oh sorry, minus W naught. Okay. That's, yes, minus W naught. Or if we are figuring out W naught, then we can maybe write minus here. But then condition will change. It has to be less than, if we are figuring out W naught. Yes, W naught has to be greater than minus of this. Minus then, okay, so then I have W naught has to be, or write W1 plus W2. This is also a positive quantity and has to be less than W naught. So these all conditions you have to satisfy. And one of the possible solution could be, we can figure it out maybe that I can take one of the values W1. So uh, so it has to be greater than W naught. Okay, it has to be W2 has to be greater than W naught, and it has to be positive, so that this I can get more than 0, right? So let's say if I take W naught as and it has to be negative also, right? So let's say if I take minus 0.5, I can take it. So this is W naught. Then W1 has to be greater than this, and it has to be positive. So it could be greater than 0.5. Greater than 0.5 I can say, but let's say I can take 0.6 or something, I can take it. Same with W2, it has to be also greater than 0.5. So let's take this also 0.6. Okay. Then another condition, W0 plus W1 plus W2 has to be greater than 0. And in this case, if I see, of course, this will satisfy, right? So minus 0.5 plus 2 times 0.6. And you can see that, yes, this condition is satisfying. Right? So you can have this values. This is one of the values. You can have any number of values which can satisfy this equation. Okay.
Sir, if I can just intervene for a second. Okay, if you're
Sure.
finished, I'll intervene. If you're moving.
Yeah, sure. It's done
Vivek,
for
that
this.
question, I think what Anupam said makes sense. Vivek, those questions have these things like, for example, a neuron must have inhibitory inputs to implement a Boolean function. It
Okay.
doesn't have to. In certain cases, it needs.
Okay.
Yeah, in certain cases, so
Right?
it depends on
Yeah,
which
so
function.
I think that all must are the words which are like red flags.
Right.
Yes.
That's all, sir.
Good.
Thank you.
Okay.
Thanks.
Sir.
Thanks.
Yes.
So W here, W has to be greater than equals to 0.5.
W has to be great.
W1, sorry. W1
yes, has
yeah,
to
you
be
wrote-
greater than 0.5. Yes, it has to be. So W1 has to be greater than negative of W0. But W0 is negative 0.5.
Yes. So it would be greater than equal.
Greater than equal. Yes, greater than equal.
Yes.
Yes, greater than equal. Correct. Okay, so for perceptron, this is the this is the equation we wanted to satisfy. But how will we learn this theta? I mean, we can definitely do this task manually. That I write some W naught, then try to satisfy all the equations. But there's a better way. We have this learning algorithm for this. Okay, that how are we going to converge or satisfy all the conditions in percept. So what we do is we take all the points we take. Some of them belongs to okay. First, there should be a linearly separable function. Then perceptron can converge for that case, right? So linearly separable is must. Okay, remember this. Is this recording on? Like session recording is on?
It is
No,
being
recording
streamed,
My
is
yes.
session
not
is
on.
recording, it is streaming, everything is
It's
happening fine.
streaming, but
Yeah,
recording is not on.
Yeah, streaming is on, right?
Oh,
Yeah, it's fine that way.
oh, recording is not on, is it?
No,
Yeah.
recording is not on, but streaming is on. Okay, that is the.
So I think you will want to switch on the recording, right? Because other people will
No, we can
stop.
see it on YouTube, right?
Yeah,
After
it will be
streaming.
available on YouTube. If
Okay.
it is streaming, and
Yeah.
Okay.
Hello.
yeah, hello. Yeah, give me a minute.
Okay. Yeah.
Uh, so yes. So
Yeah,
if
that course ID got disconnected in the beginning of the meeting, like when you started sharing here. I thought you
yes,
noticed that, but yeah, anyway.
I didn't. So that's why he got confused.
No. The streaming continues. So unless
Okay.
explicitly stopped, it keeps going on.
Okay. So if data is linearly separable, then perceptron algorithm will converge. Converge means it will correctly classify all the positive points and negative points. So let's say we have few positive points, and then here we have let's say some let's say negative points. So this is a linearly separable data because we can definitely draw a line and uh, divide them, right? So if this kind of data is there, then we can of course converge. So what we do is in learning algorithm we go for a loop. So while not converge, let's say you can write not converge. What we are going to we will pick one x of this data set, okay, and if it belongs to positive, but there's summation, right? W transpose x plus W naught you can write, which is which is which is less than 0, right? So if this is the condition, if it happens, then what we'll do is we'll have update our W, right? So we'll initialize some W, can initialize anything, but then we'll update it, right? So maybe you can write it as W dash is going to be W plus this point, right? Whatever point is there, X, we'll add that. But another case is that it belongs to a negative class, but the summation came out to be greater than 0, right? Greater than equal to 0. In that case, I'll just subtract from that. And if I continue this for some iteration, then it will definitely converge. Okay. So proof of convergence is given. I'll not do that, but you can, if you want, you can check it out.
What will be W naught here?
That is bias. What will be
Oh.
here?
Yeah, W naught here. Yeah.
Yes, what if it's theta in this case? Sure. Can we take that? No, so I think in this case we'll not take W naught as something, but we'll initialize that. So we'll have this vector, right, which will have W1, W2, let's say W3. We'll have W naught also. So we'll initialize this with some values. You can initialize it as 0 zeros. Okay, you can have this. I mean anything you can initialize, and then it will update accordingly. So in case of uh, wherever W naught is there, my X I want to add X, right, which is going to be 1, always 1. This is always 1, and then rest are whatever X1, X2, and X3. So that's what I'm going to add into. If it is going to positive, if it is negative, I'll subtract 1 from that. So that's how it is going to.
Okay, the first value in the weight vector would be W naught. Okay.
Yes, first or
Okay.
last, whichever way you can write, whichever
Okay.
way you write the your code.
Okay.
But wherever it is, so we'll add 1 whenever it is positive but incorrectly classified. If it is negative and incorrectly classified, then we'll subtract 1. for bias term.
Okay, I have a doubt in a PYQ regarding this. So can we discuss now or later?
Okay, let's discuss later. It'll be
Okay.
better.
Sir, from the exam viewpoint, proofs are not required, right? We're talking
No,
about
not
proof of convergence.
no, not that much is required.
Okay.
So
One thing just like to clarify here is that if the weight vector is not given, the convention is it is used as a zero vector, not any vector. It has to be zero vector if it is not given.
if it is not given, yes, if you can take it, but there is no question. There will be no question of that.
No, in the past there have been questions and they have been solved only if we start with a zero vector. I'm just telling, I mean, I'm just putting it out here.
Mhm.
That's normally the convention. It should be the zero vector,
Um,
just in case.
See, I'm not sure. I mean, depends on who creates the questions and all. I mean, they thought norm is. I never heard of that. This should be the norm.
You know, as long as you are
Mm.
creating the questions, it's okay then. I mean, I'll go with what you're saying, so no issues there.
Okay. Okay. Yeah, I mean, it should be given. What is the norm? That it should be, given, because I don't know what is the norm in which area, like
Oh,
what
okay. I'm
dimension.
perfectly fine. So I'll go with your clarifications, and I think that should be a baseline for quiz 1. So we'll do that.
Okay.
Got it. Thank you.
Okay. Fine. So yes. So with respect to Boolean functions, um, so that will be something like how many Boolean functions you can create using how many inputs. So let's say if you have two inputs, then you can create 2 power. I mean, n is the number of inputs, so you can have 2 power n, which is going to be, let's say, 2 power 2, which is going to be 8. 2 power 4, sorry, 16. 2 power 4 is 16. So you'll have 16 kind of functions, right? 16 kind of Boolean functions. From this, you can refer this. So this is not much. You need to go into it. Okay. Then okay. So I'll not cover it. Something next is something like representation power of perceptron, but that is also straightforward. I'll not go much into that. But let's go to sigmoid neuron. Okay. So sigmoid neuron. So what we do is we have this, let's say, neuron, and first we take the summation. Then whatever summation comes out here, let's call it as z. We take, like, the function is 1 by 1 plus e power minus z, right? So this is a sigmoid neuron, right? And of course you can have any number of this thing, and you have bias also. So some b bias you can add, right? Then it will give you output which can range from 0 to 1. Okay, so again, the range is 0 to 1, but here now it is continuous. Like, you can maybe have that's something like this. One is kind of impossible. Like, you can say maybe 0 is also kind of it is converging to that point, but it might not reach there also. Okay. So, but this is where you will have continuous um, values, continuous values. Okay. Earlier we had only Boolean values like either 0 or 1. Okay, but now you can have maybe 0.2, 0.4, 0.5, anything. Um, you might have in between 0 and 1. Okay. So this is a sigmoid neuron, and good thing about it is, so previously we had this perceptron, right, which was very hard coded. Like if the threshold crosses certain limit, right, so certain limit it crosses a threshold, then you'll have suddenly one output, or if it is less than that threshold, then you'll have zero output, right? But in reality it's not like that. You are little bit lenient in terms of decision making. So if we have these values, you you are like um, more likely to decide better, right? And since this values lies between 0 and 1, we can actually connect it with probability. So if something has something has value 0.6 sigmoid neuron, you can say maybe 60% or 0.6 probability that this might happen, something might happen. Okay. So previously we had step function, so we moved from step function to a little bit sigmoid, not from this we kind of transitioned to this. Okay. So this is just the summation that double transpose x should be greater than something. Okay. But here we'll have this sigma of this. Uh, and in this case also we can actually define what is our I mean in here it is, this is my w naught and this is my, okay. So whatever value you can decide, and above that it will be that value and less than something. So you'll have continuous value between 0 and 1. Okay. So that is the sigmoid neuron. And should explain. I think this one. Better. Just okay, so not required. Okay, so in this also you can so it's given that you can try out some values of sigmoid neuron, maybe try to figure it out what is the output, right? But that's just not what we are going to do, because we have some learning algorithm which we are going to try, right, for this, which is gradient descent in our case. And gradient descent is pretty straightforward, that uh, so whatever loss function you have, let's say you are here, you want to have this loss as less as possible, right? So here you will have some weights just defined for some w comma b, and you want to reach here, right? So you want to update your w and b to maybe move in this direction, and then you'll move further, and then ultimately maybe you'll reach here, right? If it is a convex function and you have this kind of function, then okay. So generally it converges around local minima. So if something like this and you start here, then you might reach here. If you start maybe here, then you might reach here, right? So something like that. Okay, so we'll use Taylor series for that. Uh, Taylor series approximation to actually figure out what is the formula or what is the function value at some point, right? So we're going to take a gradient. So I said that we are going to move in this direction, right? But how will I know what is the loss value around my point? I know this point, but I don't know. I exactly don't know the surface. I don't know much about anything less than this point and this value, right? So what I'll do is I'll I can actually figure out what is the value very near to that point, right? And very near to point you can figure out using Taylor series. And as much uh, this terms you add, you'll get better and better approximation of that value, right? So let's say this is my loss function, and you are here. This is the point from current W and B. You want to figure out this point. You can approximate this using Taylor series, right? So that's why we will require this Taylor series. You can have as much approximation. So, but generally we use linear approximation, uh, right, and not the quadratic approximation. So some proofs are there.
From the exam viewpoint, anything specific we need to like? Would quadratic
not
be there or?
no, just linear. No, will not do that. It's just linear
Okay.
terms. But I think you are aware of that there is a gradient descent, and this is how it works.
Yes.
I'll just if I just go through if something should be careful about. Okay. Yeah, so derivative of sigmoid, right? So you can see derivative of sigmoid is this, and later on also we'll see that when we are going to take, let's say, d dou h by some pre-activation function, then also that we get input as h into 1 minus h, right? So that's what same thing you're getting here. This is the term for that, and we'll multiply by x. There will do something else because we are not doing with w, right? I mean, if I would have done by w, then it's like something like this, right? So this part is not going to be there, but this part is going to be there for this derivation tau h by tau a. But for now you can just ignore because you will be figured out like there. We'll do that again in the full neural network. Okay.
So this slide, I have a doubt, sir.
Sure.
No. This, yeah, this one.
Mhm.
Now, suppose I've been given a problem where I have multiple points.
Mhm.
Okay, x1, x2, x3. There's a vector,
Mhm.
and I have a weight vector also. Okay, to initialize. It is 1, 1, 1 or 0, 0, whatever. I have a weight vector also to initialize.
Mhm.
Now I take the gradient. So for each point, I will add up the gradients. I'll sum up the gradients, right?
Yes.
Even as per the code, I'm going to add up all the gradients.
Yes.
Now I've added up all the gradients, and now I do the weight updation.
Mhm.
So there my weight is a vector.
Yes.
But my adding up all the gradients becomes a scalar because I've added them up. So how do I solve that?
No, you have
no.
You have, let's say you have XYZ. You're talking about the update, right? And gradient, right? How do I update when I have multiple variables? Is that what you're saying?
Yeah, if I have multiple inputs, so I have a vector of inputs x1, x2, x3.
Mhm.
And
So-
I have a initialization of a weight also, say 1, 1, 1 or 0, 0 or anything.
So Vic, I'll just change it to XYZ so that it's easier and not x1, x2, but it's the same thing. Let's say your input had X, Y, Z, whatever, let's say 5 features, right? Instead of calling it X1, X2, X3, I'm calling it X, Y, Z. That's all for simplicity, right? Your X update, Xt plus 1 is equal to Xt minus learning rate into the gradient with respect to X. Y will be Yt plus Y minus whatever, Y0 minus N into learning rate into gradient with respect to Y. You have to do it with respect to each one of them.
Correct. So see, currently we have one W, right? But if you have more W and you take derivative with respect to that, so
But here, why are we adding it up?
because we are
I have
doing
to
it
do
for
it separately.
different points, right? So first point we'll do that. Then for second point, maybe it's here. So we'll do that, and then we'll add them. And you can see from like how it looks like this. So our loss function, right? Let's say loss function is, I think you are aware of mean squared error, which is very familiar. So which is y hat minus y square, and we'll do divide by n, right? So this summation is there in my loss function. Now if I take dou L by dou W, let's say, and this summation is going from 1 to n, right? All the points, correct? So if I do that, then this summation is still there, right? So for each
So
point,
you're
I'll
saying
take.
I have to do it separately for each weight and each point. Then so I'll get a vector of weight updates. So each weight update, I put it into the loss function. So I'll get a vector of loss functions also, a column vector, and then I take the average of that.
Yeah, kind of, but not. So you will have like dou L by, let's say, dou W1, then you will have sorry, not W1 but 0.1. So W only, but for first point, okay, I is equal to 1. Then you will have same thing for point equal to 2, and so on. Then you'll add them up, okay, all of this, and of course division by n is there, because this loss function is like this. If you take derivative of it, the summation is going to be there, right?
Okay, so for every this thing, I have to take out the loss function, add it up, and divide it by the. So take the average of that. Right.
Yes. So that's how the loss is, and that's why I'm taking derivative like this also.
So this is what I want to clarify, sir. This is here xi is a data point, not a feature.
This one?
xi yi is a data point, right? X1, X2, X3, X4.
Yes, in this case,
right?
Yes, it is.
Yeah, xi can be xi can have 100 features if I want, right?
Yes, you can have it. Yes.
Right. So here it's a data point. That's what here is the question I had asked on discourse also, and you responded, sir. Whenever we take, so we are cycling across data points. We are not. This is not about features, right? It's not like x1, right? It's not like x, y, z different.
No, because
right?
this is the much more represented, right? So y hat is going to be function of all the inputs, right? Which is what phi hat is, like all the inputs, the function of that, whatever comes out.
That's what I'm saying, sir. X1, X2, X2. Then if you write it like this, these are features. This is not
correct.
This is not. So okay. So here xi, you mean what? Xi is a data point or feature?
So x. Okay.
Xi is a data point.
Okay. Yes. Here xi is a data point.
Right? So when you take a gradient, in such cases, when you are looking at multiple, see, I can update the gradient based on one data point. I can update the x1, y1 or x2, y2, or I can do it combined, right? When I do combined, I have to take the average.
No, not necessary.
How not, sir? Then let's say I have a million points, then I'll just add up the million gradients, right?
Yeah.
Yes.
So everywhere it is missed out, sir. If you can just, maybe it's obvious, that's why they didn't mention it. If you can just clarify that.
I think you need to add up all the gradients.
So I kind of figured out what is the issue there. So see, if you look at the loss function, it will become much easier. So you have this loss function, right?
Correct.
So what will be the derivative of this? You will have this all the points, right? So now I'm doing with respect to iteration. Okay, so sorry, all the points, 0.1, 0.2, 0.3, will have all of them. you add and divide by n, because a derivative also you will have n, right? Divide by, like, you take, when you take derivation, the n is a constant, it will come out, correct? But let's say you would have taken just squared error, just square, which is this, then you don't need to divide by n, because it's also not there in the derivation. So it's just formula based, like, don't think
Okay,
much
so
about
either
that.
you do it here or you do it in loss.
Yeah, so depend on your loss. So you consider loss as just squared error, then you don't need to, because you never mentioned divide by n, right?
I agree.
So if you take mean squared error, then n will also be there for all the points, because that's how derivation will come out, right? This is a constant, so it will come out for all the points, and then you need to divide by n. So depends on what kind of you take, and yes, you have to sum all of them. So here it is, they are points only, all the points, not.
Yeah. So So like at the bottom you have written here dl by w by n. Either I take the n here or I adjust for this n in the loss function. If I take the mean square error, then I don't need a n here. If I take just a squared error, then I need a n here.
No. If you no. If you take mean square, if okay, no.
So just go back, just stay on that slide, sir. That's
Yes,
a
okay.
important one. So I'm
Okay.
saying at the bottom, dl by dw, you have taken an average of the gradients. I just want to confirm that. Is this
yes, because loss is mean. So see, loss is mean square error, right? So you'll have 1 by n, then whatever it is, like let's say y hat minus y square and divide by n, right?
Correct.
Now
that's what
you'll take derivation of this, right? Derivative of this, but you will realize that 1 by n is always going to be there, because it's a constant term. I don't care much about it.
Yeah.
Right? But if it is going to be just squared error, let's say y hat minus y and square of this. If you take derivation of this for all the points, then divide by n will never come, because it was never there, right? Just summation part will come.
Correct.
Summation part, sir.
Correct.
Yes.
Correct.
So then divide by n is not required.
Okay, but I am talking about at the gradient level. Do you take n or no? You're saying it depends on how you define the function.
Yes, depends on how you define functions. You are just taking derivative. Okay, just think mathematical. You are just taking derivative, and you are going to add all the derivatives. Because
so that
is also because some function.
That is fine, sir. My argument is slightly different. I am at a certain point on the curve. Okay, and I'm looking at a gradient. Okay, I can look at one point and say, okay, let me move in this direction. Okay, or I can look at 5 points and say, okay, let me take an average gradient. Instead of relying on one point, it's like batch. Instead of relying on in batch, we will take an average gradient. We won't add up the gradients.
In average gradient, we no.
No, batch we don't take average.
No, at the gradient level, when you're computing
you
the
have
gradient,
to add up. You have to add up the gradients.
You cannot add up the gradients, sir.
I have to.
No. See, look at the sum. Look at the function, and whatever the derivative is telling you, do that. Okay. Don't think why. See, all the points are existing in a very different dimension. Let's say this is my loss function. One point exists. So from one loss, let's say 1 point, you might come out that loss function is this. Another point will say loss function is this, right? For third point, loss function is this, and like this, right? Something. So this is how you will get this loss function. But
correct.
Correct. Now for all of them, you want to reduce your loss function, and then you take derivative of this all of them, kind of, and you sum them up. Okay. Because at each point you're doing it. See, if you see the loss function formula, which is summation from I is equal to 1 to n for all the points. Okay, I'm going to take yi hat, right, predictions minus the true value, right? This is what I'm going to square of that. So square of that I'm going to take. Now, if you think what will be, and you can take mean square error if you divide by n, and if you don't divide by n, there is squared error, right? What will be the derivation of this for each point? Let's say for first point, you'll take derivation. What you will get? Y1 minus y. Okay, so this.
Sir, I got that, sir. I mean, depending on what the loss function is, you'll have to adjust for that those scalar values, right? Whether it's 1 by n or 2 by n, whatever.
Yes. Yes.
I am talking about slightly something different, which is, see, if you take the update rule, WT plus 1 is equal to W minus N into whatever del of W, right? Right. Now that del of W, if it's 1 point, there is no problem. What if I am doing it for 5 different points to take an average gradient? Should I not take an average gradient?
No. I mean,
Okay.
it's not like that. See, if you, let's say we have 5 points, okay, from I is equal to 5, y1 hat, oh sorry, yi hat, yi hat, yi hat, and yi prediction, right? This is my loss function. Okay.
Okay.
Is it okay? Now for first
Yeah,
point, take the derivation. What will you get? 2y1 minus sorry, y1 hat y1. Correct? This is for first point. Then for second point also you'll get, correct? Same thing, like what? 2 y2 hat minus y2, right?
Correct.
And for third point and so on. So for all of the points you'll get it, correct? Till
Correct.
y5 minus y something like this. So you can maybe write this as a summation of yi minus this, right? Which is what the derivation of this loss function. That's why what we are doing is we are taking so derivation of sum is sum of derivatives. That's what it means. That we are taking, when we are taking derivative of each point, we can actually sum each of them, and this is how you get this formula. And did we get anywhere divide by n? No, right? What if I would have had n in this function? Okay, what if I had n divide by n?
No, then you would get n. Then you would get n anyway. You
Yes,
would get an n.
because that's a constant. I'll never go into that, and you will have this. So then only in this case we are taking.
So can I intervene for just for a second and explain this if it's okay with you?
Sure.
So also the way it happens is if you have 100 points, you are looking at the cumulative loss. The way to look at the cumulative loss, there are two ways or multiple ways, but let's talk about two. One is a square error where you're just cumulating the loss, which is what sir has written right now. The second is you take a mean square error, for which you need a square error and you take the mean. Okay. In either case, you're always adding up all the losses. So the accumulation is happening no matter what. Okay. Now the thing is, in a mini batch gradient descent, which is different from batch or a normal gradient descent, in a mini batch gradient descent, what happens is that you normally take a group of these points and then calculate the gradient descent again and again. So Professor Arun in MLT had said at that time that in a mini batch gradient descent, you can take all the cumulative losses for each of these set of points and average them out to get an average loss, average cumulative loss, which is very different from the 1 by n here.
Correct.
Okay.
Yeah, I recall that. I recall that.
Yeah, so that is a different thing. This is a different concept. In this, loss cumulation will happen no matter what. If you're calculating square error, you don't do divide by n. If you do mean square error, you divide by n. That's it. But loss cumulation will happen. You have to find out the gradient loss for each point, like what sir just said.
And then add them up.
And then add them up. And that is a total loss, and that tells you which direction to move in.
Okay. Okay.
Better. Thanks. Okay. So, okay, that's what is my gradient descent.
Sir, I have one question here, which is that if you have a normal gradient descent, we know the formula for any question which is like on momentum or Nestrov or anything like that. Will you provide the formula or should we mug it up?
The Nestrov formula or
Yeah, momentum, Nestrov or any other gradient, different type of gradient descent. Should we mug up the formula? Will it be in the exam?
So in exam there is two in our, like, till week 4 we have, right? So week 4 we have two only, which is one is momentum and another is Nestrov.
Yes.
So I think you can remember that, like only two are there. After in quiz 2 it will be given.
Okay, got it, sir. Thank you.
So yes, because it's pretty basic, I think. Two pretty basic algorithms optimization. Okay, so okay, that's what we did. Then okay, something related to representation power, which is okay, little bit complicated, but okay. Do you need explanation of this? I mean,
So there
videos
is
are.
one question which I have to ask in this. There's
Mhm,
a lot of confusion about. So there was a question about a three-layered
mhm,
network with this
mhm,
100 towers,
mhm,
and it's in a three-dimensional setup.
mhm.
Now you go by what sir has taught. So three-dimensional setup means 2 to the power of 3, you get 8, and you require, 8 neurons to make one tower. So for 100 towers, you require 800 towers plus 1 is the output neuron. Now, a lot
Okay.
of controversy is going on. It is said that it requires 501 towers. So I'm not sure that if you change the architecture, does the formula change or what happens?
So I mean,
Can
see
we
for
just look at that question? Or can we go to discourse and look at that, Vivek? Is that possible? Because
yeah,
there's a
sure,
lot
sure.
of discussion around that.
Okay, I've not seen the discourse. I've just heard it from people around. But my interpretation was it should be 801.
So
No, somebody
I
gave a heuristic, na 2n minus 1, 5n minus 1.
something like this. Okay, so this question.
Yeah, yes, sir. This one,
Yes,
this
sir.
one.
Yes, sir. This one only.
So I mean, okay, so there is one or two confusion which might happen is related to the words which are used in the course. That first of all, this when we have two inputs, right? Uh, we are calling it as 2D. Uh, if you can see here as
Yes,
well,
sir. Two
that is
inputs,
called
2D. Yeah,
2D tower function, right? When
right.
we have two function, I mean two inputs, two kind of inputs, that means 2D tower. But it will form a 3D tower. Dimension wise 3D. It will be a 3D dimension, the tower, but the inputs are two only. So that is a confusion. But if you see, they mentioned, let's say x1, x2, and let me let's consider that. Let me also consider that this is 2D tower. That's what we are talking, not the, I mean, 3D tower for the case of it. Okay.
Then also it'll be 401, right, sir?
Then yes. So now the thing is, what happens is, yeah. So then you are right that if I put, let's say, 2 power 2, then 4, right? That's what formula says, that we need 4 neurons to create a tower.
Yes, sir.
Okay. So I think that formula is not that correct. That's what I presume, because if you go to what I want to show you is that if you go to the link provided in the lecture, I think it is the initial, yes, here. If you go here, it is much more. If we go here, so I'll just skip it till last where it was explained, and you can see here. So this is the one which we are looking into. Okay, you can maybe play around with little bit. Okay. Not very good with, yeah, but it will change. So this is the tower which we wanted from two inputs. Right? Here you can see two inputs are there, x and y. In our case, x1, x2, and you'll need this 5 kind of neurons to make this one tower, and then you will need to add them up, all of them. So from here the answer is coming 501. But then the question is incorrect because we need two hidden layers. We don't need three hidden layers. So I don't know. So that question is incorrect and answer is incorrect.
No, you will need 5 to create
A
one
tower.
tower.
Yes.
But for 2 inputs, you're having 10.
No, for this 2 towers. So this is one tower.
Okay, for 2
so
towers.
this
yeah.
one light gray box is one
Okay,
tower,
got it. So
and
it's
this another light gray box is another tower.
right.
Okay, so we'll need more of this tower. Let's say for our case, we need 100 towers of this, right? So we'll need this 5, this gray units, this gray unit which contain 5 neuron of 100, and that will make it 500. And we'll need one more which will add them up, all of them, and that is giving me 501. But in this case, I need only 2 hidden neurons, 2 hidden layers. Will not require three hidden layers.
So how do we answer such questions if, I mean, this question
That's-
is quite complicated. One, the 2D, 3D version, input is 2 and they are saying 3D. 2, it is said 3 hidden layers.
Correct. So I mean that is complicated, but let's skip it. It's not going
Okay.
to be quiz 1. Okay.
Okay.
Yes.
Wait, so no tower based questions in quiz 1?
Yeah, no tower based.
Okay.
No tower based. Yeah. I mean it's confusing. Okay. So the either we should use this exact thing and then maybe move on, but okay, for now it's not there. Yes. Let's move on to peak lecture 4, which is going to feed forward neural network. And yeah, much. Okay. So we are done with all the boring part of it. Now maybe we can do something better. Okay, so let's do the feed forward and backward neural network. So before I start, I'll explain few terminologies that when we write weight, right? Or let me draw the neural network. So let's say my this my let's say 4. So 2 here and let's say 3 here. Okay. So this is my, let's say, neural network, and let's say this the weights connecting to this guy. Okay. These are all the weights connected to the first neuron, correct? And I'm going to write that, like, let's say, so I'll call this as weight 1 because you can consider this first layer as input layer. Okay, so this is my input layer. This is my hidden layer 1. Okay, hidden 1, and this is my hidden layer 2. Okay, and this is going to be my output layer. Okay, that's how it's being introduced, and then you can have multiple layers also, not 2. You can have as many hidden layers. Input layers is going to be input layer is the first one, which will going to have neurons equal to number of features. Okay, so as many features you have 20 features, you have to take 20 neurons in the first layer. And in output, it depends on how many classes are given to you. The number of classes will define the number of neurons. Okay, so k classes, then k neurons you will require. Okay, here you will require the based on your data set. So x belongs to, say, r t, then you'll need t of this neurons in input layer. Okay, now how weights are being written is, let's say, weight 1, which are connecting input layer and first hidden layer. Okay, so input to first hidden are called weight 1. Okay, and they are being defined that this is so first for first neuron. If I wanted to write all the weights, then I'll write W layer. You can call W1. So from 1 this is coming up, or you can say layer also, that layer, hidden layer, or layer 1. Okay, then neuron 1 and weight 1. Okay, again W1, neuron 1, weight 2. So this is W111, this is W112, and this is going to be W113, 113. Okay, you don't need to take transpose of this. This is how we have defined, so that we don't need to take the transpose, right? So when usually why the confusion happens is when we did all the time, we always wrote W transpose X plus P always. But here we don't need to do that. We will just take A is equal to WX plus P. Okay, we don't need to take W transpose. So whatever way defined, this is the only way we'll always define it. So here also some confusion might happen, that should it start from 0 0 or should it start from 1 1 or something. But generally, like in course, it's being explained 1 1 1, and that is the terminology I used in exam also. So it will start from 1 1. Okay.
Because all the PYQs, last PYQs have 0.
Yeah, but I didn't saw that, and I in lecture it's starting from 1.
Yes, that's true. But PYQs
Yeah.
have a lot of PYQs have 0.
Yeah, many
But
have it.
yeah, so should we consider that we will start basically the row and column indexing is starting from 1? Can we
Yes.
assume that? Okay.
Yes, yes. Okay. So then if I wanted to write for the second neuron, which is this one, so this is my second neuron, right? Okay, so all of the weights, all of the inputs will go there, correct? So that I'll write first from this first is coming up, then neuron 2 and weight 1, 1 2 2, 1 2 3. Okay, I'll need 3 only because I have 3 inputs. Okay, for now I have 3 inputs, that's why I need 3. If I so third you can write, or maybe I write 3. Very simple. So if I write
Sir,
for
can
W2,
you explain that once again, sir? That 1 to 1, that second row, 1 to 1, 1 to 2, 1 to 3, that portion.
so this first is coming from here. Okay, which layer I am.
Right.
2 is coming from which neuron I am in that layer. So I'm in second neuron, and which weight is there for that neuron.
Got it.
So
that is from the previous layer, which neuron it's coming from.
Yeah, from which neuron it's coming from. Okay, so from which neuron it's coming from, and that's how this 1 to 3.
So, but this will be a 5 into 3 matrix. No? You stopped at 3. You'll carry on to 4 and 5.
Yeah, 4. Yes. No, there are 4 only, I think.
Okay, 4. Yeah, sorry.
Yep.
Okay.
Yeah, it should be 1 4 1, 1 4 2, 1 4 3, like this. This many neurons will require. Okay. And when we'll take so there is going to be terminology called pre-activation, in which we'll just take the summation. Okay, so Wx plus B summation part is called pre-activation. Then I'm going to take some kind of activation function, right? So for now, let's consider we have 2 activation functions, which is sigmoid, and another is 10H. Okay, this 2 only explained in the week 3, so that's why this 2. Okay. More will come up in upcoming session, but for now we'll have this 2 only. And sigmoid is 1 by 1 plus e power minus z, where z is w. You can call this. Okay. 10h is going to be. Okay, this is always confusing. I think e power minus z minus z plus e power z, something like this. So this how sigmoid and all is there. If I take derivation of sigmoid, okay, why I'm taking it, it's simple to remember. That's why just remember it. You can to it at your time, that why it is coming like that. So derivative, or if I write sigma dash, then it is going to be sigma whatever, like sigma z to 1 minus sigma z. Okay. Or you can write h into 1 minus h. So whatever h layer you are in, h1, h2, h3, you can write it. So h is always going to be, sigma of a. Okay. That's how you will always get h, and h is activation layer, okay, which is applied on pre-activation something. Then for 10h, we'll have 1 minus whatever the 10h function is, right? So you can call it as, let's say, h square. Okay, 1 minus h square. That's how you'll get derivation of 10h with respect to the activation. Okay, with respect to activation. This is also with respect to activation. Okay. Sorry, pre-activation. Both A is pre-activation. Both are derivation with respect to pre-activation, and this is how you will get this values. Okay. Now, okay, so I think we did that. Now, if we see, if I'll just write one more so that it's getting clear that what are the weights of this between hidden layer 2 and hidden layer 1. Okay. We have two in the hidden layer 2 and 4 here, right? So let's say W2, if I write first, W2 will come, then my first neuron is there, it will have one weight, first weight of that, right? W2 neuron 1, second weight of that, W2 first neuron 3, 2, 1, 4, right? Then 2, 2, 1, 2, 2, 2, 2, 2, 3, right? So this is the weight you will get as W2. Okay. And I'll skip
Can you go up a little, sir?
Here or
W2, the diagram.
okay.
Okay, right. Yes,
So 2 here and 4 are coming into that.
right.
Okay. So that's how W2 will be defined, and W3 also similarly, which will have how many rows? 3 rows and 2 columns.
Right.
Okay. So W3 will have something which will have 3 rows and 2 columns. Okay.
Right.
So,
This
so maybe
tan H formula is e to the power of z minus e to the power of minus z, or is it the other way around, sir?
I don't recall it. You can maybe look
Okay.
into it.
It's
In the exam,
e power z minus e power minus z.
Okay.
So
Other
first
way
one
around,
is
huh?
plus and second, yeah, that's all. Otherwise, the minus sign is correct. Otherwise,
Okay.
So you were saying in the exam?
It could be.
no, this
Maybe.
formula will be given, or we will have to remember.
You were saying
No.
something about this in the exam. You were saying in the exam, and then you stopped.
It could be there in the, so I mean, not for exam, but for our perspective, like quiz 1, these 2 activation functions are given, right? In the course, like in week 3, it's these 2 only.
Yeah, so normally in the exam, sigmoid, the formula is given. So will that be for TANH also, or we should again learn it?
Yes, it will be given.
Okay, thank you, sir.
It will be given. Okay. Okay. W3. Now there is, I'll skip W3, writing it. Then we are at which part? Okay, H3 also we can figure it out. Now output layer. Okay. So output layer. So for classification, we use softmax, right? Softmax, which is very easy. So let's say output pre-activation layer, which is AL. You can call it that. Let's say we get AL1, AL2, and till ALK, something like this, right? Then on that you will apply a softmax layer. You will get predictions, which we call predictions also. and that is going to be e power al1 divided by summation of all of them, right? All of them. So al1 e power al2 and so on, e power alk, right? Then same is going to be here, and then this whole summation, this part, okay? And so on for all the k term, okay? So on for e power alk
ALK divided by the denominator.
summation, right? So all of them you will get it as a output. So this what softmax function is. Okay.
Yeah, can you go up a little bit? Just a little bit up. Just that weight 3. W3 is a 3 into 2 matrix.
Yes. 3. Yes, yes, 3. Because 3, because I wrote 3 here. 3 classes. I mean k. You can write k into 2, if you like. So this k is equal to 3.
Should it not be the other way around, sir? 2 into
No.
is going to 3.
See, we had 2 neurons here. So how many rows I wrote?
Output layer, 3 into 2. Right.
I wrote
right,
2,
sir.
right?
Right.
Two rows. And in W1, I had how many neurons in this? 4. So how many rows I had? 4. 4 plus, let's say 4 cross 3. Correct? So as many neurons are there in that layer, that many rows I'll have.
Right. Sir. Clear.
So this is my softmax. Now, okay, so loss. Okay, so loss is cross entropy, which is going to be summation of my negative, and then summation of yi, and then generally we take natural log, okay, y hat, right? So whatever my predictions are, I'll put it here, and then take summation of from 1 from I is equal to 1 to k. But the good part of about this loss function is that I'll get all of them 0 except wherever it's true, right? So for some, at some point, whichever the true classes, I'll get one of this. So 1 as this, and then so left is like 1 I equal to L. L is the true class. And I don't need to take summation also, because that is the only point left, right? So if I tell you that, say I had 1 0 0, which is my true y, okay, true y, because we had 3 0, that's why I'm writing this for this case one. Then my cross entropy was supposed to be y1 ln y1 hat plus minus y2 ln y2 hat plus y3 ln y3 hat, okay, like this. But you can see that y2 and y3 are 0, so it will go away, right? I don't have it. And y1 is 1, so 1 multiplied by ln y1 hat, right? ln y1 hat, that's what left, minus of that. So that's what my loss is now. Okay, loss is minus ln y1 hat. From this, I'll have just one term left, and rest all will go out. Fine. So this is my cross entropy loss function. Okay. Now let's see what. So this was my forward kind of. I'll use all of them while doing forward pass, and I need to compute them, right? And then while doing back prop also. But before I go there, let me present this slides, and I'll just go to the important portion, which is gradients with respect to each one of them. So this was my loss, and you can see this is what we come out. So if it is going to be let's say linear or regression type of problem, then I'll take squared error loss, right? And linear as my output activation function. Okay. So this is the chain we wanted to figure out, but yeah, we'll only use this only, but we'll see how to do that. Okay, don't worry. Before that, just go through this exact, okay, just explanation. Okay, yeah. So this part, does anybody have doubt on this? Because I'll not explain while I do back propagation. Okay, so any or this part. Even if you remember this, it's good enough. Okay.
Now,
Okay.
some of the formulas will change because of tan H versus sigmoid.
Yes, if 10H, then only one formula will change, not here. When you'll take,
Yeah, only one. Yeah, the derivative one.
yes.
Well,
So
actually, all are derivatives. Yeah, but
Mhm.
the H2 to A3, I mean H to A, del
Yes,
H by del A.
yes.
Okay.
That only change. Otherwise, everything is same. Okay, and you can see. So
So what happens if the loss here is squared loss?
then this will not be like this. This will be a little different, right? So it will be going to be y hat minus y and square of that. So you have to take derivation of this, correct? And it's not going to be like this. You'll have 2 times y hat minus y. So this is what you will get for 1 point. And this all things explained for single point. Okay, not the complete
Correct.
all the
Correct.
points, right? It's
Correct.
SJD. You can consider this as SJD, and 1 point we are passing through at a time.
Correct. Sir, you had actually you finish off, sir. I had one question in this, which where I'll refer to your live session because I found that very easy to implement.
Yeah, so that is only we are going through, but I thought maybe if somebody has doubt here, I'll go complete this, and then maybe move on there. Okay. Yes. Okay, so I think that's it. But let's say you have softmax. Uh, Hello. My,
Sir.
yeah. Okay. It's okay. But so see, whenever we have soft, so we define softmax and all. Just a quick question. Let's say we had a vector. Okay. Let's say x1, x2, x3. This is a vector, and we get output also as sum of f of x1 or all of them. Doesn't matter. X1, x2, xn something. All of them, some of them. Okay, whatever, doesn't matter. And then f1, f2. Consider all of them. F3. If I ask you, maybe you can call this as let's say capital F, okay, which contain all of this values of f1, f1. If I ask you what is going to be, and let's say call this as x, df by dx, if you take, what are you expecting? What will you get? Is it a vector, matrix,
Get a
scalar?
matrix. Sir.
You'll get
Because
matrix,
you
right?
are doing a derivation of a vector with a vector, so you will get a Hessian matrix. No?
correct? So that is going to df1 by dx1. Then I'll take with respect to all of them, right? Whatever. Here 3 is there, but if it's more, then something. And then again you'll take for df2 and so on. And df3 and so all of them you'll get like this. You'll get for if you do it right. And same thing happens when we have softmax, right? But we kind of ignore that that we have a1 to a k. Then we figure out what is h, right? So some it's going to be a by summation, a2 by summation, and then so on, correct? Till ak. Then when we do, so let's say tau l by y hat and tau y hat by tau whatever a l, right? This term is actually a matrix. Okay? This term is actually a matrix. But then from this, if we multiply by this, ultimately we end up having a vector, which is this vector is actually y hat minus y. This vector you will get. So y hat is, let's say, you this vector something, right? Which are the predictions you got as y hat. Then you'll subtract y from that, and be careful in this. We will not write y as a scalar. We'll write them as a vector, right? So something like 1 0 0, right? If it is true for one class and false for all of them, then this is how I'll write, right? So let's say y1 or some y is written, which is like this 1 0 0. That means this class 1 is true and rest is 0. I can, if I write like this, then my second class is true and rest are 0, right? So that's how y's are always going to be written. Okay, so y is a matrix, this y, and y hat is also a matrix, and we'll subtract from each other, end up having this. Okay, fine. Now let's do. I think it's better to take the example and then get done with it. Better, easy to explain. So let's take this. Okay, so here you can see how weights are being explained to you. That you should take weight size x and this back propagation thing, and so this.
Maybe you can annotate on this one directly. Would that be simpler for you?
Yeah. We have it. Okay, so these are my weights. Okay, and this is what it is. Okay, now see, whenever we asked question or whenever we required this whole derivation thing, what we wanted to do is we actually wanted to figure out what are the derivative with respect to weights, right? Either let's say w1, which is all of them. Okay, all of them in this. So at one point maybe asked about a point only, but generally we wanted to update all of them, right? Then bias is associated with it, which is in this case not there, but um, but you can consider them having it when you really actually do this TL training, right? Then you wanted to do this P2 tau w3 tau by tau p3, right? So this is what I wanted to update. Okay, correct. So let's say if I do it with respect to my first one, this will come, not the this guy. These are the last one in the picture, and it's being asked that we use sigmoid. I recall it that it's the sigmoid guy. Okay, so let's see. First we need to compute what is a1, right? To find the h1, and that is going to be 101. Then the weight matrix, which is okay, 1 0 0 1 1 1 0 1 1, okay? And then bias is not given, and it's being asked that you can ignore them. So that's why I'm ignoring it, but you might have it sometime. Okay? So let's see what is.
Sir, the 101 is the inputs coming into the output layer, right?
Should be like this.
The column
Then only
vector.
multiplication will. Okay. Yes. Sorry. Inputs are. Yes.
Yeah, that 101 is the inputs coming into the output
Yes.
layer.
No, input layer.
Okay.
So this is my input layer,
Okay.
and here I'm getting 101. Okay, and then it is connected to.
Okay, so you're doing the forward pass right now.
Yeah, forward pass we have to do. Then only I can do backward
Okay.
pass. I need all these values
Yeah.
to figure it out. Okay, so this is yes, I'm doing forward
Okay.
pass.
Got it.
Yeah. So I'll need a1, then h1, a2, h2, a3, then y hat. Then I'll do the back pass. So let's see what is this going to be. Okay, one of this, two, and then again one. So this is my a1. Then h1 is going to be, I'll take sigmoid of this, right? So 1 by 1 plus e power minus 1, e power minus 1, right? Something like this. And these values are going to be, you can see here 0.73, 0.88. Okay. 73. Fine. Then I need to figure out what is my a2, which is going to be, again I need to write weights.
W2 into H2.
1 1 1. Okay, so that is 1 1 1 1 1 1 0 0 1. Okay. And then I need to multiply all this h1, not h2, h1.
Yeah, sorry. Yeah, H1.
0.73, 0.88, 0.73. Right. This is my W2 and this is my H1. Okay.
H2 is what we'll get after applying sigma to that.
Yes. So I'll add them up, which is going to be, if I add them, 6 plus 8 is 4. 14 plus 8 is 22 and 23. And again 2.34, then 0.73. Right? So this is what I'll get as A2. Then I need to figure out what is H2. Correct? So what I'll do, I'll 1 by 1 plus e power minus 2.34. 1 by 1 plus e power minus 2.34. In one of the question I saw on discourse as well.
So 0.73, right?
Sorry, 0.7. In one of the discourse I saw that somewhere given that you take like 2 of this. Okay, something like this. So in that cases, if let's say some multiple of sigmoid is given, okay, then what you can do is figure out this part only. Okay, divide by 1, and if it is just a multiple, right, you can write multiplication outside of the matrix. Why is that? So when you'll do backprop, if you do tau h2 by a2, you don't have to change much, like 2, you'll have 2 h2 into 1 minus h2. Okay, something like this you'll get. If it is multiplication by 2, if it is multiplication by some other number, let's say any c, you can write like this. It's in any previous year question, but if it's like this, you can always use this kind of derivation while doing backpropagation and easily figure it out. If it's a constant, if it's something else, then not. That will not work like that. So I figured out H2. Now I need to figure out A3, which is going to be, oh, okay, I need to write these values. Let's do that. It is 0.9191, 0.67. 0.67. Now A3 is going to be again 1 by 1 plus e power 0.91.
No, A3
Oh no
will
no no
be
sorry. This is output layer. Sorry,
Yeah.
softmax. So I'll apply softmax over that, which is not like this, but it is like e power 0.91 e power, and then divide by e power 0.91 plus 0.67. Okay, something like this.
Won't
And
it be with W3 into the H2?
oh, sorry. Yeah, it should be.
Softmax will be applied to H3, right? After.
So first I need to write this W3, then H2. Right, let's write W3, which is 100, 100.
111.
Something like this. I'll multiply it with this guy. So I'll get
0.91. 0.91.
Summation all three is 9, 18 plus 6, 24. So something like this I'll get. Then I'll apply softmax over it, which I'll call y hat, which is H3 also. Y hat is e power 0.91 and then division by 2.4. Okay, and same thing I'll do. It's summation e power 2.49 summation. This is the summation which I wrote. First. Let's see what is this. This is 0.15 and 0.7. So this is my y hat. Now, what is my loss? Loss is going to be minus of whichever y true is given. So let's see the question. If I see the one, so y3 is 2, right? So whatever my loss is going to be ln y3 hat, correct? And y3 is 0.70. So minus ln.
So can you explain this part? Where this y3 value?
Y3. This is y3.
Yeah,
right.
but
y3 hat. Why is it? Okay. Okay, let's see. So y with this y was given to me 0, 0, 1. Okay, this was
okay, yeah,
my
got
y
it,
was
got
given.
it. Yeah.
And y
so yeah,
hat
you
came
already
out
explained it that the others will get others will get reduced. So we'll just have y3 in that.
Yes, and this is what I got. So if I write like cross entropy, L is cross entropy, right? Summation.
Yes.
Oh,
so y1 and y2 will get reduced to 0. You'll just have y3.
Yes. Right. So I'll have this, and this will be 0. This will be 0. I get this value. So this is the value I got, ln of 0.70, and that value is going to be 0.35. Okay. Is it fine? So this is what I'll get. Now, okay, now I figured out the loss. Now enter to one back pass. Okay, I'll do one back pass and then I'll leave it. So let's do. first let's do tau L by first weights, which are going to be in my W3. How will I do that? I'll write the equation, right? Tau L by phi hat, because that's how it's connected. You can see here my loss is going to be like, say, this is what phi hat is, right? Y1 hat, Y2 hat, Y3 hat, and then from that I figured out the loss. Okay? All went into the loss. So I need to do that. Then Y hat, or you can call HC also, whichever you like, but Y hat is very easy to remember that it's from output. Then from Y hat I need to go inside, which is A3. Okay, A3. Then A3 is actually connected to W3, right? That's why I'm going to do with respect to W3 of A3. Now W3. Correct. Now this part I know it's going to be Y hat minus Y. Why? You can actually see percent. Maybe here if you so while taking derivatives we come up to the result that this is what is my Y hat minus Y, right? So here it's being written like Y EL, right? You can see EL is written, but if you write EL is actually it's being said that wherever my Y came out to be true, I have to write that, right? So actually this EL is like in our case, it is 001. Then from that Y hat I'll subtract that, and then I'll take the negative of that. This thing actually you can write Y hat minus Y. So it's easy to remember. Okay. You can write like this, it's your choice. That's how I explained in the lecture, but this is much easier. That it will become like this. Okay? Y hat minus Y. Far easy. Now, yes. So, so let's say if I wanted to do with respect to this weight, I wanted to figure it out. I'm going inside. This will come after. Okay, so after that, actually, this part will come up where we are taking gradient with respect to parameters, because we don't have any hidden layer, right? So at W3 we don't have any hidden layers. So I will directly jump to this part. Correct. So I'll require this part, and then last part. Because since I don't have any hidden layers in while computing W3, so I'm not doing any of this, but I'm skipping that and going there, and that's what you can see from the formula as well. That this much formula is required, right? So this part I figured out Y hat minus Y. Then if I do A3 with respect to W3, this is a little bit tricky. That what you will get is actually you'll get this H K minus 1 transpose, or in our case, if I write, it is going to be H2 transpose. Does anybody have issue with this H2 transpose?
It's clear, sir.
Oh, thanks. So now let's do this. Y hat minus Y, which is 0.15 minus 0, 0.15 minus 0, 0.70 minus 1. Fine. And H2 I have to take, which I already computed somewhere here. Not this. 0.91, 0.91, and 0.0. This is my H2, right? So I'll write that. But I have to take transpose of that. 0.67. Correct? So this is how I'll get all the values of W3. How many are there in W3? 9, right? So will there be 9 values I'll get from this?
Yes, sir.
If I multiply, yes, right? This is 3 cross 1. This is 1 cross 3.
You
If I
got 9.
multiply, I'll get 3 cross 3. Correct? If I ask you any element of S, can you figure it out? Let's say if I ask W12, where it's going to be. I mean 312, whatever. 312, right? If I ask you this part, where you will find it? 1 here, 2 here.
First, second column.
Right? 1 here, 2 here. Let's say 3, 2. 3, 2. Okay. So this guy is going to be W311. So in that case, I'll multiply 0.15, or let me make it, or I'll just write all of them, right? W311, 31, 312, 313, and so on. 331, 332, 333. So this is what my matrix is. That's what I'll get here. You can, let's do it. So this is 0.15, 0.15 minus 0.30, and I need to multiply with this, all of them. Okay, let's. So first I'll multiply 0.15 with 0.91. What will I get? I think all of them are not mentioned there. I recall. And it's correct. So I think I have to do it myself. Yeah.
0.14 you can write, sir. Just approximate.
First one?
Yes, sir.
Okay. So then again
right.
I'll get 0.14. Here also I'll get 0.14, and so 0.14. Correct. No. This guy is going to be minus 0.
Last one is going to be 0.10. The
This
first, yes, yes.
0.10. Okay, same thing here. And now I one more input. This is negative 0.2.
Minus 0.273.
Right.
Something like this, right? So this is what I'll get. If I ask you any of this point, you can figure it out, right? What is 332? How will I got 332? Third of this, second of that, right? And that's what this value is. So from this, you can actually figure out which one you want to answer. And if it would have been with respect to B, right? If there was, let's say tau L by tau B 3, then what you would have done is tau L by y hat with respect to A3, right? And then A3 with respect to tau B3. But in our case, B3 is not there. But if it were to have been there, this will come out 1, okay? And just 1, like it's not going to be matrix, not a vector, nothing. It's just 1. Okay? And it was always same thing, y hat minus y, a column vector. Fine. Now let's do it with respect to W2. This is much fun. So let's do that. So again, I'll write the whole equation, but you know it gets into the brain that this is how I write. Now from A3, where should I go?
Yeah, that'll be y hat, sir.
Oh, sorry. Y hat. Okay. From y hat. Okay. From A3,
you'll go to H2.
I'll go to H2, right? Does anybody have confusion here? Why I'll go to H2? No, right? From H2, since H2 is okay, so this is this. Let's say this was my last layer.
So now,
this
now
was,
that you're asking why H2, can you explain? Can you just?
Yeah, even I'm wondering that.
okay. So this
No,
is my y head.
actually, so got it, sir. Got it. H2 is the input of A3, right? So okay, got it.
Right. So
A3 is a in output of A2, H2.
So
Got it.
I wanted to go to this W2 guy, which is which will appear here, right? So how A3 is connected with respect to this layer is through H2. Okay. First I'll reach here. Then since H2 is connected to A2, I'll take with respect to A2. Then A2 is the guy who is related to W2, right? So that's why I'll take this all derivatives. Fine. Now this part we know. This 3 part we don't know. Okay. This part was always y hat minus y. Okay, let's do this one. What is going to be A3 with respect to H2? What is A3?
W3, A3 is W3 into H2 plus B.
Right. So A3 was W3 H2 plus B3.
B3. Yeah.
Yeah, B3, right? Now if I do that with respect to H2, you can see this is going to be 0 and you'll get W3, right? But there is a catch. If I wanted to multiply this,
okay, that is a 3 into 1 vector, and your W3 will be 3 into, I don't know what it was. It was
it is completely W.
3 into 2.
3 into 2, whatever, right? So I can't do multiplication here, but I need to take transpose of that, and then only multiplication possible, because because there is one more reason is there. One is multiplication is not possible if you write W3 here, right? If you write it here, even you take transpose, doesn't matter, the multiplication is not possible, because this is a 3 cross 1 matrix. It has to be 1 cross something, right? But it's not 1 cross, it's a 3 cross something, right? And another reason is, since you can see that this is my H2 guy, right? And this was my 3 thing, and it's going towards all of them, 1, 2, 3. When I come back, and when I'm asking with respect to A3 with respect to H2, actually I'll do with respect to here, and there, right? So 3 derivation I will have, and I need to sum them up also, so something like that. So if you get it, like it's all the reasons, but ultimately you have to take multiplication. You have to bring this W3 guy in front, and then only multiplication possible. And same thing is explained in the lecture also. You can.
So one question I have there, sir. If you go back to that.
Okay. Give me a minute. Okay. So I'll just show it that when you take derivative with respect. Yeah. So this is what I was explaining, that chain rule is happening along multiple paths, and that's why. This is what I'm talking about. That's why I'm taking W3 transpose and then the derivation with respect to loss, right? Whatever this guy. But this is what I have to do. And this being explained here because I have to do multiple paths, and it's not possible because one more reason is that multiplication will not happen if you put it on the right side. Okay. Yes. Yeah. Go ahead. What is the doubt?
So when we, let's say here, the doubt is what this W3 is the original weight vector row wise or column wise. See, because for our theory, you already said that W is already transposed, right? So that you directly take W3 into X plus B, right?
Yes.
So for example, when I compute A3, will I do W3 into H2 plus B2, plus B3? Just write
no.
A3.
So see, A3 is W3 H2 plus B3.
Yeah.
right?
So this W3 is already transposed because that's how you gave us, right?
Yes.
So when we do this, we have to transpose this weight matrix, right?
Correct. So this is transpose of this.
Okay, because
transpose.
see the I tried to figure this out, but many of the problems in the PYQs, that W3 is a kind of a symmetric matrix. It doesn't matter whether I transposed it or not, right? So I couldn't figure out whether it's correct or not,
No,
right?
no, it's
But I
correct.
just wanted to confirm that this W3, because in some literature outside, those weights are actually by column, and then you take W3 transpose even while calculating the A3 value or whatever, A1, A2, A3. Whereas here in our theory, you've already done that to make it simple. So I just wanted to confirm that we do have to take the transpose. Okay.
Yes, you have to take it, and if you let's say, so in our case, we will, I think, okay, in this example we can't, but if it would have been not symmetric, then you will realize that okay, let's see. So we have 2 here and 3 there. Will it work? Okay, let's say 4 here. So my this W2 is going to be 2 cross 4, and okay, I don't care about that. W3 is 3 cross 2. Okay. Yes. Now let's see. Okay, so W3 is 3 cross 2. Is it okay? I'll not write all of them. Now let's say if I do W3 multiply by this whatever y hat minus y, what is going to that? 3, right? So
3 cross
I'll
1.
have 3 cross 1, right? This is 3 cross 1, and this is also I'm just not taking transpose. This 3 cross 2. Will this multiplication happen?
No, this won't work.
This won't work. What if I take transpose of it?
Yeah,
will it
it
work?
obviously will work. Correct.
So, and you'll get 2 cross 1 output, right? So you can figure it out this way also. So yes, I have to take transpose, right?
Got it.
Okay. Yes. So I'll take transpose and then multiply.
Yeah, because our W is already, because our W3 is already transposed, is that you can directly do W3 into H2
No.
plus B. I got confused whether we should do it or not.
No,
this was
but yes. So you can maybe figure out with the dimension of the matrix that multiplication will happen or not.
Yeah.
If it doesn't happen, then it will not work, right? So in this case, it will work because here it's symmetric, or you can say maybe
correct,
square
correct.
matrices. Okay. But other
no square. See, at least values were different. I would have checked with the answer and figured it out. But it was not only square; it was also symmetric. So there was no way of.
Yes. But you can see, right? Multiplication.
Now it's clear. Now it's clear.
Okay. So from this, I get this part. So I kind of wrote this guy here, not here. Okay, but there. So this is what my multiplication is, and you can figure it out. You can cross check my answer with this part. Okay, this is what I did. I bought my W3 in front, then only multiplication is possible. Correct? Okay. Okay, let's we can do that. Then let's figure out this guy. What is what is this guy? It is sigmoid, and I'm taking with respect to input. And guess what? This is, I have to take element wise multiplication I have to do. So this matrix I'll get something, right? Something I'll get here, and then I'll do matrix element wise. Be careful that I have to first multiply this, okay? Then I'll only move to next, because after multiplication, my dimensions of or I'll not get square matrix if it was not like that, right? So in this case, you will not realize, but I think you are right. I mean, we should have given some kind of question where it was not a squared type of matrices or symmetric matrices. Okay, but let's do this. So this guy is sigmoid, and if I take derivation of that, I'll get H2 1 minus H2. Okay, this is also going to be column.
Yeah, it's a 2 cross 1.
column, right? Column matrix,
Yeah.
column vector. Or whatever.
It's 2 cross 1 column vector, right? Because there are two neurons there. No? H2 has, if you go up.
No. This we are still in the example. I think this guy. Okay, so we are into this, so we'll have 3 only.
Okay.
Because see H2, if you can see H2 is my this was my H2.
Okay. Okay.
We are solving this example here. So H2, then I'll take 1 minus H2, and then finally last guy. Okay, with respect to W2, what will I get?
So this W3 is 2 cross 3, right?
No. For now, everything is 3 cross 3. We are into this.
Okay.
We're here.
Got it.
This is what it is.
Right.
We are solving this.
Right.
Yeah. So what is A2 by W2? What will come out here? It is past 9:30, but 9.
H1 will come. Transpose.
H1 transpose, yeah.
H1 transpose, right? So here we did H2 transpose. Where was that? This guy. H2 transpose we did. Okay, now we are at H1 transpose. Just in case. So let's do this. What is W3? W3 is 1 0 0. Oh, I have to take transpose of it. Okay, just doesn't matter though. No, could matter. 1 1 1. Then 0 0 1. Then 0 0. So this is my W3 transpose. This guy I already computed. Here. So this is my phi hat minus 5. 0.15, 0.15 minus 0.30. Okay. Let's do this first. Then we can move on. Element wise we can do after that. Okay. So what is this?
0 will come. First one.
0. 0.1.
Then minus 0.3. Then minus 0.3.
Right.
So first element will be 0.1, right?
0.1.
Is it minus 0.20 or minus 0.16?
First, this one is 0. Just 0. Because I'll do multiplication with 1, add plus with respect to like this guy with respect to here 1 and right at that a row of this column of that and do multiplication. Fine.
H2 we've already done.
H2 and H2, right? H2 we already done. So I don't need to compute it again. That is the good part of it, of backpropagation, that I'll just go back and where was my H2? Here, 0.91, 0.91, 0.67. That's what I'll write. So then I'll subtract out of 1, right? 1 minus H2 and multiply.
0.09. 0.09. 33.
Then so element wise, here I have to do element wise, right? So I'll have 0. Then okay, what is this?
Excuse me, sir.
Yes. Yes, yes.
So the last element of the second vector that you wrote, that 111, that multiplication, it was 0.15, 0.15, and below that, is it minus 0.3 or 0.2?
0.3.
0.3.
0.30.
Yeah,
0.3 on.
okay. So yeah, so that is why I got confused. I thought it was 0.2. Sorry.
Because my so my y hat came out to be 0.70, right? So from that I subtracted 1.
Yeah. Okay, so I got it. That 3 was looking like a 2 to me, so yeah, my bad. It's
Yeah.
fine.
Y hat was that one. Yeah. Okay. Yes. So
this will be minus 0.024.
024 minus 0.024.
The first one will be 0 only, sir.
Oh yeah, first one is 0. Sorry. 0.024. Okay. What is this?
6. 0.33. This will be minus 0.066.
0.066.
Right.
Okay. So this is what I got. So if I write here 0.4 minus 0.066. This is 4. That's all. Okay. And then I need to multiply H1 transpose. So H1 transpose. This is H1. This is H1 0.7388. Correct. And then again, if any element I ask, you can definitely do it.
Right.
2 1. This is 2 1. 2 2. So not this 2 and 2. Right. So you can definitely do any element from this only. Like you don't need to complete all of them. That's what I'm asking, because any one of this, or maybe 2 are asked, not all of them. So it's you can skip rest of the multiplication and just do whatever required. But our case, we can do all of them. So let's do first is 0 to the first, the whole thing is 0. Okay. Now some multiplications I'll get, or I'll leave it to you. You can maybe do it. Okay. Just this part.
Yes, sir.
You wish,
There
you
is
can do it.
still one element left in the chain, right? For the calculation, or is
Which
the
element?
entire chain the chain you written on top? Well, one or two pages before.
On page.
So a bit more.
Okay.
Can you go up a bit more? A bit. Yeah, this one. The so after the yellow circle, there's one more A2W2 left.
It's here. This one. H1
Okay.
transpose.
Oh, sorry. I didn't see it. Thank you.
Okay. This guy is here. This both is here. So that's how it came out. Now I'll write the last one, and let's do. So I'm not doing the multiplication here. Okay, you can figure out all of them. So now let's do the last one, which is with respect to W1. Okay. Now what is that? I mean, see, you can. I always write all of them because I am teaching you, but you can definitely skip it. Okay. Yes. So y hat by, it's connected to A3. Then A3 is the guy which is connected to H2. H2 is connected to A2. A2 is connected to
H1.
H1. Then H1 is connected to A1. Then A1
one is connected to W1.
Right. So that is the long chain I'll get. Then I'm able to compute this. I know. Yes, I know. Y hat minus Y. This guy is A3 with respect to H2. I'll get W3 transpose.
Right.
Transpose, and but I have to multiply it in front, right? Now this is sigmoid, so I'll get H2 1 minus H2. Fine. What is this? A2 by H1. I'll get
W2
2 transpose, right? But in front. Then here is H1, 1 minus H1. So if I solve all of them, if I write all of it together, it's going to be W2 transpose. Then I'll get W inside this. Okay, wait. Not writing it from there. W3 transpose, or I'll have y hat minus y, which is going to multiply with W3 transpose. Then I'll do element wise multiplication.
H2 minus 1 minus H2.
Into 1 minus H2, right? So, and then I'll have this guy W2 transpose, which I wrote in front. So all of that in front. Then element wise multiplication of this one, right? W2 transpose, right? So element wise multiplication with what?
H1
minus
1 minus H1.
1 minus H1. The last one is what?
H0 transpose or X1.
X, yeah. So X transpose, or you can maybe write H not transpose. Okay. So this is what you have to solve in the end if you want to figure out the last layer. So in this you can maybe take help from the previous thing. Maybe we did till this part. So this much you might get help from that where we did it.
What is this H0 transpose?
X input.
Okay, input.
Input. Okay. Yeah. So if you have any problem in this whole thing, I took same example, same thing in week 3 live session. Okay, and I personally think I explained it there better than today, and you can maybe look into it.
Sir, if it's a sigmoid neuron with MSE loss, it's gonna be two terms, right? It's not gonna boil down to y hat minus y.
Then it's going to be different here. This guy is different.
Yeah.
And
sir, but can we expect a question like this for quiz 1 or?
Yes, definitely. I mean, that is the only thing which has a which makes sense to have a question, that what is backpropagation and forward propagation, right? So full pass you are supposed to know, definitely.
So this would be similar to the PYQs, right? Every step is broken into separate questions, and
correct.
Is how it would work.
Correct. So here this is what written.
Okay.
And in PYQ, I mean in solution or somewhere it's been broken into one piece of it, right? But I think it's much easier this way. If you know what each term is, then it's far easy to compute all of them together. Fine.
So I had a question for internal calculation. Like, how many decimal places should we take? Should we restrict ourselves to like 2 decimal for each step?
Yes. For quiz 1, take consideration till 2.
So rounding off for 2 or truncation of 2?
Doesn't matter much because the range will be much better. Like it will be little better, like wider.
Because the number of decimal places will determine like what final value we will have. Right?
Correct. You will have it different, but we'll consider. So we'll have a good range. Don't worry.
Right. And another thing, this particular formula that we derived in the end, it was because we had a cross entropy loss, we had a softmax in the end, and we had a sigmoid neuron, right?
Yes. Correct.
Yeah.
Cross entropy loss. Yes, that's right.
Y hat
Um,
minus y will change based on whether we have a cross entropy loss and a softmax fine output activation.
yes, it will change based on what we have here. So it will
Right.
not be like this. It could be something else.
Okay. And for the internal neurons, if we have a tan H, then the H2 1 minus H2 will change.
Yes, then I would have written 1 minus h2 square.
Right.
If it was 10h. Or here it is 1 minus h1 square, right?
Right. Right.
And this is going to be vector only. I mean,
Yeah.
the whole thing. Okay.
Right. Right. And one final doubt. So, like in this case, we had H2 into 1 minus H2. So, in a sense, we are doing element-wise multiplication for these two as well, right?
Correct.
So, if H2 is a vector and 1 minus H2 is another vector, so we are doing an element-wise.
Yes, element-wise multiplication.
All right. Thank you so much.
Okay. So this is the last thing, and you have to solve this, okay, for figuring out what is tau L by W1, and you will get all the elements. You will again get whatever your weight was initially, like that is the dimension it will have. So here we have 3 cross 3. You will get this as 3 cross 3, and then you will get derivatives, right? So after getting derivatives, what you do is whatever your weight is, let's say W1, I'll call it W. I mean, here my 1 is different, like timestamp 1, okay, timestamp or iteration 1. What you'll do is whatever weights you had, or operation will happen like new. Let me make new much easier, right? New will be going to be W old. Old is whatever I did. Then I'll take some learning rate, and then this guy, right, which I figured out with respect to what old, right? With respect to old, I was able to figure out my derivatives, and this guy will come here. So that's how my weights will update in backpropagation, right?
So any default value of eta we must assume, or it will be given always?
Given.
Okay.
Eta is given. So this is learning rate, right? Some learning rate you will be given that. Okay, fine. So this is what a forward pass and back prop is, and that I think is the whole thing. And yes, so now, yeah, these two guys you have to kind of look into it. So e power z minus e power minus n, and then summation of it. Okay. Okay. Now last part of it. I'll go there. Which is what is principal guess. Why this is coming back? Sure, but okay, contours and all can we figure it out? Okay, so we have two kind of optimization technique. One is momentum based gradient descent, and another is Nestrov accelerated gradient descent, right? Two only. And you can see the formula is pretty forward that we wrote that W new, right, is going to be whatever W old was there minus some learning rate time, the derivative, right, tau L by W. But what we are saying now is instead of doing that, this guy, right, this is actually this old one. Okay. Yeah, do that, but remember what you did even before that also. So we are accumulating it in every iteration, storing them, uh, and we'll have some weightage over it. So how much should I consider from my recent update or recent gradients, right? So recent gradient will have more weightage. You can say one, right? And here beta will be 0.9. Generally, we'll take beta as 0.9, right? So we'll have that portion of my previous weight, correct? And that's how I'll update. So you can see now my old and new are like this. So WT plus 1 is equal to WT minus learning variable UT. The UT guy is now a little bit different. So I'll have some beta parameter, and I'll take previous UT and add my current term, the gradients, right? Or let this let it be like this only, WT, right? And that's how the updation will happen. And if you see for few iteration, let's say U0 will start with uh, W0 and U minus 1 was 0. So in that case, what will I get as U1? Beta times U naught, which is this person, right? Then with respect to W1, I'll take gradients. So I'll take gradients here. So I do backprop and find this. So this I found using backprop. This I found using backprop. This also I'll figure out with backpropagation whenever I do it. So in that case, I'll have this function. Then if I want to figure out U2, then again I'll do beta times U1. So you can see U1 is this, and I'll multiply that by beta, and I'll figure out the current gradients, right? So I'll take again gradients and update my U2. So it doesn't end at U2, right? I need to do, let's say if I have U2, what I'll do, I'll have my weight 3, right? W3 as whatever my W2 were minus learning rate time U2. Correct? That's what I'll do at W3. If I want to figure out W3. So here it's iteration, okay? Not the W3 2 which we use in while doing backpropagation. There it was layers and something, but here it's timestamp. So maybe t equal to 3 or iteration, not timestamp but iteration. Okay? So, yeah, like this. So it's pretty straightforward. If you remember this formula, you will be able to figure out how to expand this. Okay. This is also same formula. If you want to recall it, that's a little bit tedious. This is much easier to remember, right? This is much easier. Whichever you like, right? And you can see that as we increase in like iteration, we kind of lose that value in that. Okay, so whatever W0 we computed, it initially it has a lot of say in the updates, but then gradually it will decrease, okay, as we do more and more iteration. But W0 will now contribute very less at higher iterations, right? And some about that. So okay, so this is can maybe play videos and all and see into it. Now with NAG, this is so what we are doing is we in momentum base we were having, let's say, t plus 1 is, oh no, sorry, before that I should mention ut, which is beta times ut minus 1 plus gradient of this, right? So we had this part. Now what we are saying is first move by this much, because either way we'll have this, right? We know this before even reaching to that iteration, or you can say. So first move by that much, whatever, wherever you reach, doesn't matter. Then take gradients there. Okay, so now take the gradients and then to move in that direction. So it's straightforward that earlier, previously we were moving this much. Let's say the total is this much, and out of that, let's say this much part was by previous gradients, and this is my new gradient. Then what I'll do is first I'll move by up to this much. Right? This much I'll move, and then I'll take the gradient, and then I'll decide how much I want to move. Should I go in this direction, or let's say should I change the direction also? Possible, right? So it might change direction also. So first take this and then move, right? So it has a better look ahead. So first I'll look ahead, and then I'll decide should I go there, like should I move in that direction. So this will help us in having less oscillation. So oscillations will be reduced. Okay? Help of that, and it's straightforward. So since we moved by this much, we need to subtract that from the weights, right? So see, you know that weights are going to be like matrices, right? Something like this. If I figured out this much, and you know, qt and all, if you know that it's going to be wl by w, this, right? And we when we solved our example, you know that this also has same dimension, right? Not different dimension. And for now, you can maybe consider it as ut or something. Let's say ut, right? So ut, this wt, all of them will have same dimension. Nothing will change there. So actually, you can take subtraction of that. So this just matrix minus matrix. Okay, nothing fancy. It looks difficult, but it is just matrix subtraction of matrix. And wherever we reach, whatever value we have, this value, whatever value we get, I'll take gradient using that. Okay, fine. So now previously, let's say I was multiplying somewhere, W3 transpose in my previous example. What I'll do is I'll not do that. I'll do W3 minus whatever this U3 or not U3 but U2, right? Whatever U2, I'll have same matrix. I'll take transpose of that, and using that I'll do the back propagation, right? So for while doing back propagation, I'll find, using that only I'll find this gradient, right? So there I'll use this transpose instead of this guy, correct? And that's what it changes. Look ahead is that only, and you'll have less oscillation. Fine. So here also again we take beta in 0 to 1. Generally we take it as 0.9. Very coarse, quicker, fine. So stochastic and mini batch, simple. Stochastic is we take each point and then update the weights. And in mini batch, we take some points, like let's say 100 points, 1000 points out of all, let's say 10,000 points I have. If I take 1000 points only and do the weight updation, that is mini batch. Full batch is the complete thing, the vanilla gradient descent, right? This is always like you would have learned this in MLT and all. Nothing changes here. Maybe you can remember this, but you can figure it out also. It's not difficult. Okay? That vanilla batch will have one weight updation for one epoch. Stochastic will have n updation for one epoch, and mini batch will have n by b updates for one epoch. Okay. Yes, you can definitely do SGT way momentum also, SGT way nag also, mini batch way momentum, mini batch way nag, right? So that you can do. Just so I let you know that we didn't change anything with learning rate. Learning rate was always eta, right? We never changed in this, and that's what we are going to do next, right? After doing some updation here. Now we'll do something. Now we'll do something related to learning rates. So let's see. There are some tips that can be given, but there's no sure shot way. Okay? What you can do is you can maybe try all of these values, and whichever values comes out to be having less loss, you try around that value, right? So it's like kind of hyperparameter tuning. You choose all this learning rate and then try, then do finer search, right? Some various types of learning rate. One of that is let's say step decay. So after few epoch, you can have some rule that I'll reduce it by this much, half it, 1/4 it, 1/8 it, or any subtraction will also work. But be careful, don't go in negative. So anything like you have to reduce it somehow. Okay. So after but generally it's this is the step decay that we half the learning rate and after some iteration, right? Here that's what being mentioned, and maybe you can go with this only for step decay that will half the learning rate after some epoch. So epoch will be mentioned what epochs you take. Exponential decay. Since this is also easy, let's say if I take neta 0 as 2 and k as let's say 1. Okay, so initially what I'll have is 2 power, let's say t equal to 0. What I'll have 1 only. 2 power 0, which is 1. Yes. Okay. What is going to be neta at another, like 2 power minus 1, which is 1/2. Okay. Then n2 is going to be 2 power minus 2, which is 1/4. So you can see maybe I started at 1, went 1/2, 1/4, 1/8, something like this, right? So we are decaying exponentially, kind of, right? So you will somewhere see like this also, that something like neta 0 e power minus kt, and actually here it's being mentioned neta 0 minus kt. Somewhere you will see this, but for this course we'll use this one. We'll go with this function, and you can actually figure out, because e is nothing but 2.71, right? That is also constant. Neta 0 is also constant. You can have it in some way, so that you might end up having this formula. It's not that different, but for this course we'll go with the mentioned formula that neta eta is eta 0 minus k. Eta is equal to eta 0 minus k. Okay, another one which is decay.
Can you repeat that last point, sir? I mean, we'll go with this.
I mean, we'll go with this formula. Will not. Okay. So I mean, see, somewhere exponential decay. I mean, on internet, or if you have studied somewhere else, you might see that it's been mentioned like eta e power minus kt, something like this.
Okay.
But if you see, e is also a constant.
Yeah. Correct.
Right?
Correct.
So it's just a multiplication of them two. You can have in any way.
Okay. Sir,
not change much.
is there a restriction on k? Should it be like positive or can it be ideally?
Can it be negative? I don't think so. You can take it negative, because then it will increase the learning rate. I mean, let's say you decided initial learning rate as 3. To take it positive, it will go up, right? Something.
Correct. Yeah.
So I don't think so. You should do that. I mean, either you should start at high place. Let's say you maybe initially take, let's say 5, which is that's a high number, but then don't take k as negative.
Got it, sir.
Okay, what is 1 by t tk? Okay, another formula, same kind of function you will get. Okay, so if some question is being asked, like generally we don't ask you to remember that much, but at least you should know little bit about what it is, right? What kind of decay is which one. Okay, this is with momentum, so beta parameter, which we initially in said that you can choose 0.9, but using this formula you can figure it out what value of beta is a good one. So so in this case, what's actually happening is we are taking minimum of max b max beta max, and you can choose any value here, right? Let's say if I choose 0.999 and I'm taking minimum of that. So unless this value is higher than 0.99, I'll always end up taking this guy, right? So let's say if I start, I mean this whole term before the comma is, let's say, 0.2. I mean some mathematics you can try, and it is 0.2. Then in next iteration, because you can see t is here, it will increase. Okay, so it will maybe increase to 0.3, then 0.4, and it will keep going on, and at 0.99 or beyond that, if it will go, then we'll always end up having this guy. Okay, so you can say we are increasing the learning rate as we do more and more iteration. So initially we'll have initially we'll have beta as less value, or you can say we are not much more confident about our history, that my history is good, right? As we accumulate more and more history, I'm also considering more and more of that history also. So initially I'm not considering much history, but later on I'll consider it, right? So if you wanted to do that, you can apply this whole formula. Okay, right? Yes, okay, this is a line search where uh, we take some values, compute all of them, then we figure out which has the least one. We choose that. Again, we go with the lowest loss of out of all, right? So which will of course increase the computation, but you might end up having better loss. So it's like um, so convenient for a maybe gradient descent, that it can choose which loss function, which eta value it wants to have the minimum loss. Okay, 4 or 5 options are always there in front of it, like, okay, choose this one, choose that one, something. So whenever you retain the updated values of w, which gives the lowest loss, right? Yeah, use the best eta value from the available choices. So available choices will be there, and you are choosing best out of that, right? So at each iteration, I think that's all. So that is week 4. I'm done with the session.
So this is the longest revision session in deep learning history. I mean, very good. I mean, I'm very happy to see the session. Just saying that thank you for putting all the effort. Really appreciate it.
Thanks.
So actually, I had one doubt, sir. When we look at Nestrov versus the regular momentum based, I mean, computationally, I understood how to do it. What's happening? How is that? Probably it's because of notation or the t's and t+1. How is it really looking ahead?
How is it looking at?
Yeah, so I
see, we first moved, right? Let's say, oh, I actually same thing I explained in last session also, okay. And I think so. See, you are here, right? Okay,
correct.
Now I moved here using history.
Correct.
Okay, so this is what my look ahead. I already did it. Did I computed any gradient for this? Any new part? Anything new computation I did?
No, I
No.
didn't.
Now I will do. Right now I will do. I'm here and now I'm doing the what um, gradients. Right now, so now I'm computing gradients. So this history part which I accumulated and using it to move in certain direction is look ahead.
But how is that? How is that history WT minus beta UT minus 1? That's what I'm not able to tally.
Okay. So as I mentioned, right? So let's say when we take gradients, right? Let's say dou L by dou W.
Correct.
We'll end up having some metrics or
Correct.
something, right? Now initially or let's say whatever my initial W's were there. Okay. Now I'm making actually let's say T equal to 0. Okay. Fine. Now I will subtract this part from that. Same dimension. Can I do that?
Yeah.
This part I can do, right?
Correct.
Yeah. Okay. Now same thing. When I'll go for let's say more iteration, maybe T equal to 2. Let's say W T equal to 2, or let's just go in U only. Let's say U T equal to 2. What will I have? Beta time U T minus 1 plus W2, right? So I mean del W2. Correct. So I'll compute gradients, but what is this guy? Which I computed previously, and this also has same dimensions. I subtract that from what W2 because I already moved by this much. I mean that's what neg is, right? So first I'll move this much. This much I moved, right? So I mean, how do you let's say let's say I have this y y is equal to mx plus c, right? So this is my equation, right? Right. Now can you tell me what is x value here if I sorry, if what is y value here if I give you x? Can you do that?
Yeah.
If I give you x, yes.
Now I can. Yeah.
Yes, right. Now let's say if I tell you if I give you x equal to let's say something 3 or something. Now if I tell you what is x minus 3, can you figure it out at that point, this y value? If you know at maybe all of them, if I write, so this y is equal to 2x plus 3. Fine. I don't know what kind of it is, but let's say x equal to 1. I gave you that. Can you figure out y for that? And yes, it is 5. Correct. Now if I tell you what is I mean x minus let's say 5, what is going to be the y? How will you do that? X minus 5.
Yeah, I can just substitute. Yeah, I can.
You can do that, right? So now so that's what we are doing actually. That we have these weights, some weights. From that we are going to reduce. From that we are going to subtract this beta time ut minus 1, and then at that point whatever L is there, I'll have loss derivative with respect to that. I mean value wise it's like that.
Okay.
So in this loss function diagram, that's what we do. We were here using history, we moved, and that's what this part is, subtraction part. Okay. Then at this point,
Sir,
I'll
this
again make a movement.
this
Yes.
momentum brought in the oscillations, right? Because we are kind of getting propelled by the history. So when we overshoot, it's it's not going to be, basically we can't correct it at that point. But with this one, when we overshoot at that epoch itself or at iteration itself, we know that, okay, we have overshot, so let's the gradient will point in the opposite direction.
Yes, that is true. So when we are, let's say, when we're moving here like this, but when we move or we pass the minima, right, the local minima, then then what will happen is we will have gradients in opposite direction now. So yes, that will lead us to in a better direction. Okay.
And since the most recent slope has the most sort of weight in the history vector, it's going to
Yes.
course correct faster.
Yes. So I mean, does it matter there? No, right? I mean, see, after one, see, history part we already did, so it doesn't matter. Now we will only move using direction and the gradient of that, right? So once we moved by history, we'll not again move by history. So now after moving by history, we'll just take in the direction which was given after that.
Yeah, yeah.
Okay. Yeah. So, bus, go ahead.
Sorry, is this completed?
Yes, the session is. I mean, from my side, it's
No.
completed.
This question, if it's completed, I just have another question.
Okay. I think so, right?
Yeah.
Yes.
So,
Yeah, go ahead.
So this is about the difficulty level of the exam. Let's say as compared to the last exam, will it be like same, more or less?
Not sure. Yes.
I mean,
It is
the
going to
paper
be
is already
same
set
level.
with, it'll be at the same level.
Same level, or maybe little bit difficult. Not sure that, but I felt that it is little bit difficult.
Oh, that's true. Thank you, sir.
You mean last quiz, sir?
Yes.
As in last quiz 1 of last term.
Yes, last term quiz 1.
Okay.
Actually, I didn't say that. So last term, the course instructor who took the quiz 1, I showed him the paper and he said it's tough than last, so I'm taking his vote.
Sir, why such
Not that much.
Why such affection for us, sir?
No, it's not that much difficult. Not affection.
Just a
just a
yeah, just a comment. It's a funny comment. Thanks.
Fun.
So another question is that will there be partial marking? So like I know in the past there has been multiple instances of partial marking where if we explain the steps, etc., we get partial marks.
Not sure about that.
So you can check Discord. There are many posts on that where.
Yeah, I saw that. I mean, I know that there was partial marking and such that.
Because in degree level, I believe in every course, in degree level only, they have institutionalized some concept of partial marking. Just wanted to check.
So as I
not
recall,
for all courses, but certainly for this one and for AI. At least for AI, I have got
there
a
in
partial
software
marks.
testing also. It is there in a lot of other courses.
As in,
Okay, possible, yeah.
You have to go and explain on discourse, is it? Because there's no way of explaining it while we do the exam.
Yeah, it'll be in discourse. You post on discourse what steps you took, you give the details, and then show how you arrived at your answer. And then the instructor decides: is this fair? Is this not fair? And then
that. Okay, we'll see. Let's have the exam. If something like that will be there, I'm not sure because.
So this is not about a question which is ambiguous or something. Is about a person who did the steps. Let's say he forgot a minus sign somewhere, so his answer is totally different. But he understood the concept and everything. So that kind
Okay,
of
okay.
thing, not a regular stuff like in MLP or some place. This happened and that happened.
Okay, see, that much
Not
will consider. Okay, that much I
okay.
will consider definitely. So if it is like very minute mistakes, like
Yeah.
-1 or I don't know some C parameter not added, I'll
Yeah,
take into
exactly.
consider.
Yeah.
Okay,
That's what I was
that
talking.
much I'll not be unfair.
Yeah.
But if it is like I got 3 and answer is why is it 0 something, then I'll not consider that much.
Got it.
So can we get some marks towards the final grade from the programming assignment?
Fine. Sorry. Repeat again.
The programming assignment.
That is a +5 bonus, right?
Some bonus
Okay.
is there,
5
right?
marks.
All
You
right.
get 5 marks for that.
Okay, so this notes I'll upload in the portal.
Thank you, sir.
Is there any doubt?
By tomorrow, right? Before quiz 1.
Today only. I'll
Sir, I have
Yeah,
one
yeah,
question from graded assignment 5. The question 5, if we don't want, if somebody has got it right, understood, they can share it in the group also. I'm happy to just look at that, because when I was looking at the explanation, I found a little bit of an error in that, in the graded assignment solution, right? So I'm not sure. If you just go to the
week 5.
Week 4, sir.
Week 4.
You can actually see the supplementary content. I was not getting the answer right.
Question number?
Question 5.
Okay, I need to compute.
No, if you just go to the supplementary content.
Okay. Oh, it's there, huh?
Yeah, it's there. Graded assignment solutions. Week 4.
Okay, so
here, just go through the. So if you come to you're going through, sir, or waiting for me?
No. I'm looking at it. Yeah, wait a minute. So, okay.
So this W10, first of all, this W9 minus beta U8, this is correct. Then we are going to W10, which is W9 minus beta U. It should be mu9, right, sir? I mean, there is a mistake here.
Where? B9? B10?
Yeah. No. For look ahead, W10 is equal to W9 minus beta into, it should be mu9.
It's U. All of them are U. Okay.
U9 or mu9. Yeah, U9. It should be U9, and U9 has never been calculated.
That.
Or am I getting it wrong? I mean, I just don't.
W9 minus current minus. For look ahead part, they are taking it.
So you have to calculate the look ahead, right, sir?
That was previous term only, right? So you're saying we never computed U8, is it?
U9.
U9.
And it's very unclear. Just go to the question, sir, or just go at the top. See, consider, suppose the model is trained, U8 is given, W9 is given. So what is the look ahead here, U9 or U10? U9 is the look ahead.
That is correct.
So
For
U9
okay,
is
so state of error 10th. So 10th iteration. Okay, so 10th is my update, right? So W10. That's what I figured out. So
yeah, but before doing W10, I will do W9 minus beta U9 to
U9, yes, U9 I will require, and in U9, that U8 will be there.
yes, U9, U8 will be there. So you come down, sir.
Okay.
If you see here, since U9 is equal to beta U8 del U9 minus beta U8, this is correct.
Okay.
This is the look ahead value, W9 minus.
For Sigmoid.
But others who have also answered can help. It's not that. So this should be U9. So U9 has never been calculated. So I don't know what I'm missing.
U9 is never calculated. Is correct. So we wanted U9. So first, I'm here. So I'm here. So let's look into this. So we need U9. So
Correct.
for this guy, right? So here W10 to W9 minus eta time U9, right?
Yeah.
So U9 we wanted to compute, which will be from beta to 8 plus I'll take gradient of whatever 9. No, not sorry. Yes.
Correct. That's 9.
No, correct. So W9 minus some beta time U8.
Correct.
So you're saying U9 was never recomputed.
Yeah, directly went to W10, and W10 is.
We have to calculate the gradient to look ahead. This part. So this is my shift. This is my left ahead, and here I'm taking gradient.
No, that is the look ahead, right? W9 minus beta U8 is the look ahead, right?
No. But see, look ahead is here because this is history. I moved by that much. This is my history, right? History is look ahead. So I'll look, then I'll do the gradient. So here I'm taking gradients. So that thing I think is a mistake here.
No, sir. Last time you said this is the look ahead.
Gradient of look ahead. I mean, so this is actually looking. I'm going forward, right? Looking there and then taking gradients. That's how it is.
Okay, I'm now confused.
No. See, this history was always look ahead, right? I mean, see, that's what we talked that first we'll move by that much. Look ahead. Oh, whatever. See, it doesn't matter. It's just the names. Don't worry. So this is history and this is the gradient we have to compute. Fine. Don't worry. So I'll just call history and gradients. Right? So we have to calculate the gradient. Fine. Of course, Sigmoid neuron with given loss. So it will depend upon phi hat at look ahead. W9.
No, now that we've moved to W10, W9 beta U8.
No, here also U9 should be there.
Correct. So U9 has not been calculated at all. That's what I'm not able to understand what I'm missing.
So they wrote U9 directly as this a thing, but for that we'll need U8. I'm not sure. I didn't solve this, but okay, I'll look into it. That would be much better,
Sir,
than
can you
scribbling
respond
here.
which part is look ahead also? If you can just put it on discourse tomorrow, it will be very helpful. So there's one problem
Yeah, sure.
my head couldn't get.
Okay, I'll look into it.
Sure.
I will look ahead and I'll tell you tomorrow.
Okay. Look into it and tell me it.
Yeah.
Okay. Sir, can you, if you're done with the video, I just have 2 minutes. Sir.
Sure. We are done. If there is should I stop the streaming? Okay.
Sir, can we expect the backpropagation
Yes.
question